assignment. In case there's anybody who has attempted the assignment, it would be nice to see what you tried to do. And the other thing is, as usual, we are going to give you 7 minutes to download information. But remember, you hadn't finished with Dr. Helen Namaweje. So she's going to continue with the survey sampling. But as part of day 5, there is some new material for you to download. And in case Dr. Helen finishes what she has prepared for you, then we will touch day 5 material. Okay, so you know where the link is, the same link, it is updated. You can go to that link and open the link and download day 5 material. At the same time, let me pick the link and paste it in the document, in the chat and Q&A so that people can access it. Otherwise, you're welcome. Pay attention, there's more to receive as far as knowledge is concerned. Thank you very much. And at 10:10, Dr. Helen Namaweje will come in with more survey sampling. Thank you very much. Going. Oh, I forgot to mention the survey mark. Let me mention it. What time would it be? Okay, good morning, participants. Today we are also going to have an evaluation for the 5 days. Today is the 5th day. We need to know whether we are doing well or we need to improve. So we will send out an evaluation 15 minutes before the end of today's training. So when we send out that evaluation in the chat, please, you fill in online. Please make sure you fill in the evaluation form. We will also announce at the end, 15 minutes to the end of the training, for you to fill in the evaluation so that we know what areas are difficult, how can we improve, etc. Thank you very much. Okay, so I just
can hear me. Good morning. Kindly confirm to the chat if you can hear me. Okay, okay, thank you. Now, we are going to start from where we stopped yesterday. I remember yesterday, before we ended, I had introduced overview of sampling, and we looked at some specific definitions, for example, what a population, what a sample is, and then we went ahead, we looked at different sampling approaches. And when we ended, we're supposed to move on to we stopped at multi-stage cluster sampling. So now today we are going to proceed, but I want us to first clearly understand what is the difference between primary and secondary sampling units. For those of you who have conducted surveys, I guess maybe this information might not be new, but it is important. I mean, learning doesn't end, so we keep learning. So with what I'm trying to mean here is that initially, if a population is divided into several large clusters of elements, so the initial stage of sampling, we call it the primary sampling units, right? And following this, when several primary sampling units are selected at random, so from these selected primary sampling units that are used into smaller units, we call that stage as a secondary sampling unit, because what happens, we do the sampling again. So we start with the primary sampling units where the initial sampling stage is done. And then in case you do the sampling again among the primary sampling units, then we refer to that as a secondary sampling unit. That what? They can't see me. All right, let's continue. I would encourage, in case there are questions, please post them in the Q&A. My colleagues are on board, and they are more than willing and happy to respond in case you feel something might not be so clear. So just post in the Q&A, there we can quickly track the questions and then they are answered. Yes, when we're moving on to this slide, this is what I've just mentioned about the primary sampling units. Sometimes it is abbreviated as the PSU, and then the secondary sampling unit is abbreviated as SSU, and so on. So like I said, with the primary sampling units, this is the first level of sampling. And at this particular stage, we include all the target population. Everyone within the target population is included. But when you move on to the secondary sampling unit, it implies that here only the enumeration areas or the clusters that were selected at the primary sampling unit are the ones that are included. So it is from primary, then secondary, and so on. Of course, there are some other like tertiary sampling units, but I'm not going to look at that. What my main interest is on the primary and then the secondary sampling unit, because these are the common ones used. So we need to understand that how to select a cluster or a primary sampling unit. Remember, if you're dealing with a cluster sampling approach, all the clusters belong to the primary sampling units. So these are the two mainly common approaches that can be used. In case you're considering a simple random sampling, then it implies that all the sampling units, the primary sampling units, have got equal probability of selection. And this particular case, that is an equal method. In case you don't use that, you can use what we call a probability proportional to size approach, PPS. This is also a very common approach when you're dealing with the different approaches of sampling. So with the probability proportional to size, it implies that the probability of selection depends on the size of the primary sampling unit. So what do I mean that it depends on the size? It implies that in case you've got a larger size, then it implies that the probability, in that case, the probability will be high. In case it's a smaller size, then the probability of selection will be smaller. In other words, the larger the size of the primary sampling units, the larger are the probabilities of selection. Okay, this one mostly applies in case we are dealing with unequal probability method. All right, so when it comes to probability proportional to size, it's usually mostly preferred when it comes to cluster sampling, mainly because of various reasons. But the main ones are because in case larger areas, they are more likely to be selected, then it implies that larger presentation of the population will be gotten. And in this particular case, though, it will be less costly. And at the same time, the secondary selection units also have got the same selection probability. So like most of the time, in case especially when you're dealing with a large group, you can do fast with, in case you're going for cluster sampling approach. After that, you find that maybe some of the clusters are big compared to the other. So then you can move on and use the probability proportional to size, whereby in that particular case, the clusters that you've picked, which have got a big representation or big elements or more elements, you can pick more compared to the ones that have got a small representation. Now let's move on to non-probability sampling techniques. Under the non-probability sampling techniques, of course, like yesterday, we looked at the disadvantages of probability sampling techniques and then the non-probability sampling techniques. But all these ones, everything has an advantage at the same time. And there is a question that, is it possible to include everyone in the population at the primary sampling unit stage? The answer is yes, it is possible to include all the elements or all the units that you are considering at the primary sampling, unit. And in case you're looking at, if you're looking at a simple one-stage cluster sampling, like I mentioned yesterday, we include all the elements within the cluster. And in that particular case, our clusters that have been chosen, they act as our primary sampling units. So the answer is yes. All right. Now let's move on to non-probability sampling techniques. Of course, there are very many, but what we are concentrating on in this particular case, we are mainly looking at the ones that are commonly used or that are the ones that you can easily apply. However, at the back of your mind, you have to look at the pros and then the cons. When it comes, so the first example for the case of for the case of non-probability sampling techniques, we have what we call convenient sampling. Okay, remember, and most of the qualitative studies that maybe you'll come across, if in case you're trying to explore them, they use what we call non-probability sampling techniques. And one of the methods they use is convenient sampling. Yes, we are saying that in this particular case, the selection is often subjective. And as a researcher, you don't need to have a sampling frame. Let me just give an example. For example, in case you're looking at a study that is trying to look at customer satisfaction, maybe let's assume that you're in a bank. Okay, you're a banker. Somebody, maybe a manager, wants to find out the customer satisfaction in the bank. So what he or she can do is just maybe to stand somewhere within the bank or at the entrance or anywhere, position himself. And then as the customers get in or as they receive services, he can quickly, ask them about their feel of the services they get. So that is convenient sampling in the sense that, the customers are there. It is also convenient in terms of time and then the place. This person carrying out the research is within the bank, and the customers come to the bank to pick the different services that they've come for. So that is convenient sampling. Or on the other side of the coin, maybe you want to find out, let's consider, for example, a supermarket still, and you want to find out if the customers still are satisfied. As a researcher, maybe you can stand at the exit of the supermarket, and you talk to this as customers come in and move out. You can talk to them, you know, whoever comes in or whoever you feel that can really give you the information that you want, because they are picking from the same services. So that is convenient sampling, and it can still be applied in different fields, especially when you look at it in terms of time and in terms of the location that you're conducting the study from. Then the other example, another approach under non-probability sampling techniques, we have what we call purposive. Okay, under purposive, some people call it, another name that you could use is authoritative sampling or judgmental. It is also a non-probability sampling technique. And in this particular case, the way you hear the word purpose, okay, so you can, for example, you can set your interest on a certain group of people. For example, maybe you can look at a group of farmers who are growing cassava, or there is yes, there is a new cassava on market, and you really want to hear about their perception towards maybe how it is grown, how long does it take to mature, and you know that maybe these farmers are stationed in a certain place or in a certain village. So purposively, you select this village where these farmers are, and then you go there and ask them about how the cassava is performing, whether it is good or it's bad, and so on, depending on the questions that you want them to respond on, and so on. You could be, maybe you want to deal with, purposely you want to deal with students, and you want to ask them about maybe whether they like the blended learning approach, or for them they like physical or online only. So purposively, what you can do, since it's the norm today, you can pick a certain university that does both blended and then that does both physical and then online learning. And then you get to the students and ask them about their feel of the blended approach. So that is purposive sampling. Okay. And then we have also another approach. I say there are very many, but I'm just looking at the ones that are commonly used. We have what we call the snowball sampling. When it comes to this one, this method, this approach is usually used when it comes to sensitive populations. For example, the drug users and then the prostitutes. Maybe you want to have a feel on how the prostitutes are treated during their work. But then most of the time they have got specific positions. Maybe you can get their leader, and then when the moment you get a leader, this leader is the one that you use. In other words, you get a contact person. So the contact person, you start with only one person, and then this person leads you to other people, okay, within their chain of work. Even the same case applies to drug users, because like we know that, well, in some countries, I mean, taking certain drugs, it is illegal. So you can get somebody who takes drugs in a certain area that you know where they are best. And then this person gives you the gospel of where you can find other people that belong to that same category. So that is snowballing sampling. And like I said, it's usually used to hidden populations, or we call them sensitive population. You start with one person, and then this other one person enables you to get to other people, or which I'm calling units that you can include as within your sample. All right. Now, so those are the three ones that I've looked at, but you can look at others depending on your study, especially in case you're doing qualitative kind of work. So let's look at, of course, when you're conducting out any survey, there are some ethical issues that you have to put in mind. All right. Well, for example, you need to have a consent. If you're going to go to the field, or you're going to meet your respondents, you're supposed to have a consent. You're not going to force people to do what you want. And you're supposed to know at the back of your mind still having a consent, and then people are supposed to voluntarily participate. It shouldn't be by force. Otherwise, if you force them, you're going to get biased results. So you also have to ensure that in case you're dealing with sensitive topics, how are you going to approach your respondents? The issue of confidentiality is very important. Sometimes, for example, in case you're looking at data, in case they give you, in case you're getting secondary data, how do you ensure that people's names or unique numbers are really are kept, and in case the public gets about the data, cannot quickly identify who this person are. You're also supposed to look at the legal requirements and also the feedback of data providers. It is always important such that the moment you go into as you're going to do your surveys, we are going to look at data collection. All these things are really very important. Ethical issues, even when you're writing a dissertation, there's always a portion about how did you go about the ethical issues during your data collection. So these are some of the things that you can look at. Okay, now let's move on to the principal steps in sampling survey. Of course, when we're looking at the various principles, number one, you're supposed to have what the specification or the objective of your survey. Like I mentioned earlier, unless you know the objective of why you're carrying out a certain study, it is very, very important that your objectives are very smart. They are smart, such that because they're the ones that are going to guide you on how you're going to collect your data. So the objective of the survey is very important. You're supposed to indicate what is the purpose of the study, at the same time, the characteristics of interest. Those things have to be identified. How are you going to construct your sampling framework, and what sampling design or approach are you going to use? Because in that particular case, of course, it will all depend on the cost that you need to use. And at the same time, the accuracy is important as you're going to try to get the final estimates of the attributes that you want to use in your study. Also, the other thing is about organization of the field work. You know, it is always important that as an individual, when you're moving out for field work, there are some things that you need to know. I mean, it's not that you're going to just go the field out of the blue and you even don't know exactly what you want to correct, okay? So maybe in case you need some little training, or you need to do, for example, a law play with a colleague to exactly enable you to say that, am I really going to do it the right way? It is always very important. And also when it comes to designing the survey instruments, for example, the questionnaire, the interview guide, or the observation guide, all these things are very important, such that by the end of the day, the moment you get to the field, it becomes very easy for you to get the data that you want. When it comes to the issue of a questionnaire as an instrument, you're going to go with, sometimes it is important to do a pilot study. Why is it important? You want to ensure that in case now you go to the target population that you want, you get the exact answers that you intend to get. Otherwise, if your questions are not clear, or you get the answers that vary from what you wanted at first, then it implies that the results that you're going to get at the end of the day, they're not going to help you to make the right or the proper decisions that you wanted to inform your audience or the different stakeholders. And also, you have to, at the back of your mind, you have to know that what kind of analysis and reporting am I supposed to be done? And all this depends on the design that you use and the information that you've collected. So those are the principles that you have to put at the back of your mind in case you're looking at the steps in sampling survey. Okay, great. Let me ask in the chat, are we still on the same page? Can I move on to sample size and power proportion? Okay. Okay. Thank you. I'm seeing the responses. Now, let's move on to sample size and then power estimation. Then at the end of the day, we're going to move on to R and see how can you calculate a sample size or a, sorry? Okay, we are going to move on to sample size and then a power estimation. And then after this, we'll have a look at how do we do it in R. There's a question, but Prof is answering it in the chat. You can make a follow-up. So according to 1977, saying that in planning of a sample survey, a stage is always reached at which a decision must be made about the size of the sample, okay? And the decision is important. Too large a sample implies waste of resources, and too small a sample diminishes the utility of result. So the point is, as we are moving out to do our, as you're moving out with you to conduct a survey, you need to know, well, how many respondents do I need? What sample size am I going to consider to include such that I'm able, and not too much, not like it shouldn't be too large, at the same time it shouldn't be too small, because by the end of that day, that one will also distort your result. So most of the common question that you need to ask yourself is that, what is the appropriate sample size for my study? Because our studies are different, but what is the appropriate size? At the same time, what is the size of sample which I can use to generalize the results of the population which I'm going to study? These are the questions that should come at the back of your mind as you're trying to estimate a sample size. Of course, there are many possible answers, but some of the answers that could really answer, in case you're looking at what is the appropriate sample size that you can consider in your study. Number one, you need to consider what is the purpose of your study, what population size are you looking at, what is the risk of selecting a bad sample size, and at the same time, what is the allowable sample error. Yesterday, we discussed a margin of error, which is the same as the sampling error. However, these are the possible answers. I said possible, but of course they could be other reasons as to why you want your sample size to be 10, to be 5, or to be any number that you want. So when you look in literature, according to Maulis and the Merchant in 1976, in addition to the purpose and the population size, there are 3 criteria that are usually needed in case you want to determine an appropriate sample size, and they are really very important. Number one, you need to look at the level of precision. I've already discussed this earlier, but I'm going to go into details. And then you have to look at the level of confidence or the level of risk. It's the same thing. And you have to look at the degree of variability in attributes being measured. When we're talking about attributes, it means that what are the variables that you're picking from the field or that you're going to consider within your study. Variability in terms of degree of variability, what should come to your mind is the variance. How do they vary from each other? So looking at the level of precision, like I say, these are just, it is just a language that keeps on changing, but the point is that I'm driving the point at home. The level of precision is sometimes also known as the sampling error and then the margin of error. So that one should not confuse you. So it is the same thing. And most of the time, it is the range in which the true value of the population is estimated. Okay, when it comes to the level of precision, it's just a range because we are not so certain about where the true value is going to lie. But when we are coming up with a conclusion, you can say that, okay, in case the true population, for example, is 60%, you can say, giving a certain allowance, say, and conclude that our true population 60% with a level of precision of, for example, plus or minus 3, plus or minus something. But most of the time, like what I said yesterday, yes, it is expressed, the range is expressed as a percentage, and in most studies that we usually see in literature, the cutoff is plus or minus 5%. But some people still further, depending on the study that you are looking at, you can still even go down, for example, to plus or minus 3% or plus or minus 3%. That is our level of precision or the margin of error. They are just the similar terms, but at the back of your mind, you know that when you're going out to collect data, sometimes it's not that you're going to pick all the targeted population. So as you're picking the sample, you're bound to make certain errors. But it's just like I mentioned previously, what is the allowable one of the reasons was the allowable sampling error that you want to consider. Okay, now let's take an example. We are still looking at the level of precision, call it the margin of error. So there is one here that if a researcher finds that 70% of the students in the sample have adopted a recommended practice of submitting the assignment with a precision rate of plus or minus 5%. Precision rate is the same as the margin of error, and it's the same as the sampling error. We say it's expressed in percentage form, and it's just a range of a plus or minus from the true, from the estimated true value. So then he or she can conclude that between 65% and 75% of the students in the population have adopted the practice. So this was just an example, and wanted to find out whether students will really adopt to the recommended practice of submitting assignment. This could be at the university, and the researcher found out, like, well, from my findings, 70% of the students have really adopted the recommendation. However, we need to there is a level of precision of plus or minus. So implying that if we subtract from the 70, we go by, that is be 65, and then in case we add, that will be 75. So that is the conclusion, that between 65 and 75 of the students in the population have adopted the practice. We are trying to see, how do you derive the level of precision, call it the precision rate or the sampling error. And then the other one is the confidence level. Remember, among the many reasons on how you can determine the appropriate sample size of your study, apart from the purpose, the sample size, now the key ones, the things that you really have to look at, apart from the level of precision, we also have what we call the confidence level or the risk level. Most of the time, the confidence interval is based on the central limit theorem. So this should not confuse you, but what does it mean is that when a population is repeatedly sampled, okay, you can sample like maybe 10 times or 20 times in a particular population, depending on the study that you're looking at, or the purpose or the objective of your study. You're within a population, you can sample like 20 or 10 times. All right, so we are saying that the average value of the attribute obtained by those samples is equal to the true population mean. Because remember, if it's from the samples, we get it is from the samples that we pick that enable us to come up with a conclusion for the entire population. So when it comes to the central limit theorem, we are saying that if you repeatedly sample, have different samples, all right? But end of the day, when you get the average, assuming you pick a sample and you want to get the average height of students, okay? Maybe we can have like maybe 10, let's say 500 students. Maybe you pick the first sample you take, it's for example of 60, you pick another one of 80, and so on. So in case you get the average of all of them, then it implies that that will give you a true population value. And then on the other hand, the confidence interval, it's also expressed as a percentage, and most of the time statistical and also from literature, we use a 95% confidence interval. But you can go ahead and use a 99, or you can use 90. But in this case, we are considering 95%. An example that you can take, that if a 95% confidence interval is selected, what does that mean? So it implies that if you're using 95% confidence interval, in case you have 95 out of 100 samples will have a true population value within the range of precision that we specified earlier. So we are looking at it in the way that in case you had 95 samples out of the 100, so because you repeatedly selected them up to 95, then it implies that if you take the average of them, you are going to have a true population value within the given range of precision or the sampling error that you chose earlier. Okay, let me check in the chat. Are we on the same page? Can I proceed? All right. Okay, let's continue. Now, the other one is about the degree of variability, and this refers to distribution of attributes within the population. Okay, so the point is that the more heterogeneous the population is, the larger the sample size that is required to obtain a given level of precision or a given level of sampling error or the margin of error. And then the less the variability, that is the more homogeneous the population, then the smaller the sample size. So most of the time, like I mentioned earlier about how these attributes vary from each other. The point is that how can we ensure that we reduce the degree of variancy amongst the attributes that we are having. So let's take an example. We're having a proportion of 50%. Okay, let's take an example. Assuming I'm having a proportion of 50%, okay, indicates a greater level of variability. I'm looking at different percentages. I've got the one of 50, that the 50% indicates a greater level of variability than either 20% or 80%. Remember in the example that I showed earlier on the precision rate, where we said that the students were adapting to a certain recommendation on how they can submit in the assignment. So why I'm saying that, why is it that 50% indicates a greater level of variability? Because if you said that maybe, for example, 20% and then 80% indicate that a large majority do not. In this particular case, 20% do, and then 80% do not. And then when you look at the 80% in this particular case, 80% do, but then the other 20% doesn't. So in this particular case, it becomes a little harder to tell now which the degree of variability should I put into consideration. Because if I'm considering 20% that do not, then it implies that the majority, the 80% does. If I consider 80% for them to adopt to the new recommendation, then it implies that it's only 20% that doesn't. However, for us to have a trade-off, we like to get a case where both cases are considered. In case we take a 50-50, in the sense that whereby if we take a case of 50%, in this particular case, 50 do adopt and then 50% doesn't. So that is, we are looking at it in terms of the halves, 50% do and then the 50% do not. So in this particular case, the point is that the 50%, it gives us the greater amount of viability that we can consider during our studies. And most of the time, for those of you who have read in some of the literature, they consider the degree of variability as 50%. And this is the maximum variability that is being considered by most of the researchers. And of course, there's also some literature that backs up the degree of variability to be equal to 0.5. In case you're carrying out, if you're writing out this section, especially in the methodology of chapter 3, of the dissertation of how you can get your sample size. Sometimes students tend to submit in, for example, they say, I'm going to consider my margin of error as this, maybe plus or minus 5. I'm going to consider my P as 0.5. But the point is that you need to also put an argument. Why did you go ahead to consider the 0.5, such that as your supervisor or your instructor goes ahead to read, even you can also author some literature that I'm going to consider this for this particular reason. You don't just come out of the blue and say, I'm going to consider maybe 20% or 80%. You should have a reason as to why you're considering that. So our maximum variability that we can consider in our studies is 0.5, or you can consider 50%. All right, let's move on. Now let's move on the various strategies. Okay. In the chat, there's a question about clarifying more of the variability. I say that when you're moving out, when you're going to the field, right? Remember, you're collecting data on different attributes, or call them variables, or call them elements, and they are distributed differently. So, and I mentioned that in case you're dealing with if you're dealing with a population that is more of heterogeneous in nature, which is usually the case, then in that particular case, you'll have to consider a larger sample size. So the point is that when it comes to the degree of variability, you're looking at how are these attributes, how do they vary from one another? Because it's a variable, there is a change. Okay, because when some people are conducting the study, they might say, I'm going to consider the variancy between my attributes, for example, to be 20% or to be 80%, or some to be, for example, 50%. But there should be a reason as to why you look at this particular distribution. The point is that depending on the sample that you want, in case you're dealing with, if you're going to have the sample that you're considering, it's more homogeneous, then it implies that in that particular case, you're going to come up with a small sample. So when it comes to the variability amongst or between the attributes or the variables that you are going to consider, how do they vary from each other? It is also very important, because by the end of the day, it also contributes on the sample size that you're going to consider at the end of the day. Like I mentioned, you can, sometimes we base the results on literature, but the maximum variability that we usually consider in surveys or during research, it is 0.5, whereby you're considering a certain group that maybe, if you're looking at a certain variable, you're looking at 50% might say yes, 50% might say no. So you're looking at a trade-off point that is half-half for the case of the variability that you consider during your sampling as you're collecting the sample size. All right, now let's look at strategies for determining a sample size. Of course, there are various strategies for determining a sample size, okay? There are many approaches, but what we are going to look at here, sometimes in case you want to, you're determining your sample size, you can using a census in case of a small population. All right, so in this particular case, you can use the entire population as a sample. Remember, I talked about the primary sampling units. And then, but in this case, with a small population, what I mean is that, for example, it could be less than 100, but not beyond, less than 200. You have to also look at things in terms of cost and then time. In case you want to look at a bigger population and you don't have money, because most of the time the economical issue come into interplay and the issue of time. So you can use a census if you're considering a small population. And then also, in case you're doing sometimes when we are doing research, most of the studies that we are trying to do, some similar studies have already been done. So you can also consider, when you're in your literature review, remember most of the time when you're writing out your proposal, you do some literature review. So as you're reviewing literature of other scholars, you might read through those who have done similar studies and see what sample size have they used, and in what ways can you use such that you can also relate to your study that you want to do. So even similar studies can support you in case you want to come up with the sample size. Also, when you look at, there are a lot of published data out there, published tables that talk about sample size, whereby already the studies have been done, and then within various compulsions, and they have come up with certain conclusions. For example, in case you consider the Yemen formula in Yemen 1967, there is already a published table which has got the sample size, in case you want to use a certain sample size. They give you different levels of precision or the margin of error that you can use. And usually it's between 3% in case of 2% and in case of 5%. And also, so you pick according to the range that you want to consider from the published data. But still at the same time, you're supposed to indicate the source on where you or how you came up with why you considered that kind of sample size. All right. Also, we can, continuation, you can use what we call formulas. There are various formulas that you can use, but we are not mathematical expression of formulas, I might say, but we are not going to go into the details. In your own free time, you can maybe Google and find out how they work. We have the coherent formula, the Yemen formula, and then we also have the common formulas for the sample size for the mean or for the case of proportions. But the coherent and the Yemen formulas are the ones that are commonly used in case you're calculating the sample size. So in your own free time, you can decide to Google out how these formulas work and then use them. So I'm going to use the last bit for the case of what about the formula for sample size for mean and then the proportions. Still, it's a Yemenis formula that I looked at. Okay, like I said earlier, if you check in the textbook on page 86, it states that n is equal to the z. We know that the z value, that is the z value, which is usually at 95% confidence interval. We've got the population variance. Just a second, there are questions that is convenient sampling more relevant for qualitative research? Yes. Like I mentioned earlier, we are going to move on and look at data collection techniques or the different types of research. When it comes to qualitative data, remember most of the time with qualitative, you want you use approaches like interview. You do in-depth interviews, and those are in-depth interviews whereby you meet somebody and then you discuss at length, or you're trying. Let's consider maybe you're trying to find out about a certain drug, and these patients got this particular drug. So you're trying to, within your study, you're trying to ask these patients how when they got the drug, how did they feel, or did they feel any change? What was the impact on their bodies and so on? It's like you want to get a story. So in this particular case, it will be, you will only consider these particular people. Okay, you're going in for qualitative interviews. So the answer is yes. When it comes, most of the qualitative research, we use non-probability sampling approaches, and convenient is one of them. So another question about purposive sampling. I talked about purposive sampling. The point is you need to know with purposive from the word like the target, what is within your target population, what is the purpose of your study? In case you want to find out, for example, maybe there is a new variety, the example I gave, that there is a new variety on the market, a cassava variety, all right? And you know that the farmers in a certain village, let's call it village A, they're the ones that growing that kind of variety that you are really interested in. So what you're going to do as you're carrying out your sampling approach, okay, you're purposively going to select that village because it has got the people or the farmers which you want to include in your sample, because they're the ones that they grow the kind of cassava that you want to study about. So purposely, you don't go to village C or D, but you go to village A, because you know these are the people that grow cassava that you're studying about, or the cassava of which you want to know, how are they faring? Is it, for example, are the soils favorable that they are getting the right yield? And also maybe you might want to find out the constraints or the challenges the farmers are really facing in planting that particular yield, that specific yield. So that's why you have to go in for purposive sampling. Okay, and then there's another question: is 5% a mandatory level precision? Well, like I mentioned earlier, it is the cutoff. Most of the studies we consider 5% as the level of precision, but we have seen other studies that consider below. In other words, it's a cutoff. We cannot go above 5%. Most of the time, you can consider, for example, you can consider 2%, you can consider 3%, and so on. Like I was talking about some of the published tables for Yemen. You find that in the different published tables, you're going to find a column. They will give you a sample size. And then in the next column, they'll ask you, in case you're considering 3% level of precision, if you're considering 2% level of precision, and then 5% level of precision. So in that particular case, it depends. If your study is very sensitive, then let's talk about maybe if you're dealing with human beings and, if you're testing, if you're dealing with human beings, you really shouldn't put a big margin of error, because somebody's life is delicate and you don't need to face other challenges thereafter. So the cutoff when it comes to the level of precision is 5%. However, you can consider other levels below that. Like I mentioned, you can Google out the Yemen formula published article when it comes to the different sample sizes. You can go in for 3%, for 2%, 5%, or 4%, just there. Patients, how do you get the sample size? Well, I don't know whether I've gotten this right when it comes to the patients. Maybe like you can consider the approaches that we used. The simple random sampling, the one that is commonly used. Okay, let's assume that you're doing a study maybe in a particular hospital, yeah, and you randomly select all the patients that will come in that particular day. You assume, in case you're saying you're using a simple random sampling, you can consider the first patient, and then maybe you randomly pick. So that is, it will be up to the end that you want, the size that the size that you're going to choose that you want. In case you're considering systematic sampling, like I mentioned, most of the time you have to, if you're sampling the systematic sampling interval, in case you're saying that you're going to pick after every second, or after every fourth person, usually the 1 up to 4, it's a random, it's a random selection. You can pick the first person randomly, and then you say, in case your N, you want it maybe to have 20 patients, then it implies, if you want to have 20 patients within your sample, it implies that if you pick every fourth, so as you count among these 100, the moment you get to the 20th patient after every fourth patient that you take, then it implies that that will be your N. Those are each nth person that you'll pick, you'll include him or her in your sample as a patient that you'll consider in your study. Okay. Then the other one, yes, how do you know variability before you carry out a study? Like we said earlier, because by the end of the day, like I mentioned, well, if case you're dealing with a similar study that is already conducted, you can consider similar literature, and then you consider what level of variability did they use. But most of the time, like I mentioned, from literature and the published articles, our level of variability, we consider it as 0.5. You're putting into mind, like you want to consider a certain percentage that, for example, maybe if you're looking at the degree of satisfaction, maybe 50% of the population of the sample that you'll have will not be certified, and then 50% will not be certified. And then, but however, remember, you can do data collection, but at the same time, you can still go back and resample again in case you see that what you've collected has not yet, the sample that you have, when you try to test out the result, do not align with the results that you want to get at the end of that day. Okay, so those are the questions that I've gotten. What is the best time to conduct a pilot survey? So the point is that we need to understand what a pilot study is. When you're having a study, all right, or you finally, you've designed out your questionnaire. Let me use the survey instrument, the questionnaire as a survey instrument. You've completely constructed out your questionnaire. But remember, you as a person, you might not really have enough knowledge, or saying that maybe now my questionnaire has exhausted all the things that I want. Sometimes you can sit, for example, in a group of maybe 3 to 5 people, you discuss out this questionnaire according to the study that you're looking at, and get also other inputs from these different people, maybe from people with the same specialization. They might give you certain hints and tell you that, you know what, maybe what about in case you also include this, you might miss out this important information. All right. So having put, in case you shared out your questionnaire to somebody else, in case you are a student and you discuss your questionnaire with your instructor, of course, I mean, with his guidance or our guidance will tell you, well, in case you've constructed this particular question, I think it will be much better in case you phrase it this way. So let's assume that you've received all the inputs within your questionnaire. Now, that is the time whereby now you do what? You can go and do a pilot study and test and see, is it really, are the results going to get really correspond to what you want to get from in the final survey? And most of the time, it doesn't necessarily mean that the people that you go to are the ones that are the ones going to be in your study. But what you can do, you can just get a similar population that you want to consider and get a feel of what they are going, of the answers they are going to give you. And then from there, you can conclude and say, yes, I think now I'll be able to get the right result or the right responses from the population I'm going to consider. So still, the pilot study enables you to improve your instrument or the tool that you're going to use to collect your final data. All right, I think the questions I've answered them. Let me check in the chat. I've answered that. Some of the questions I've answered them. When it comes to qualitative work, we don't have margin of error, because the margin of error, most of the time, it is attributed to probability sampling techniques. We don't have mathematical background concepts involved, let me say. All right. Now, I was talking about this formula. The formula, I say there are many of them, but I'm only looking at the commonly used ones. When we are looking at the Yemen formula, we have N, which our N is the sample size. The Z, that is the Z value at 95% confidence interval. And we still know what Z is when we read the statistical tables, 1.96. So at least we are not going to change that. And then the sigma squared is a population variancy. And then our E is the E squared is the margin of error, call it the level of precision, call it the sampling error. So those terms should not confuse you. So in this particular case, in case you've put you know the margin of error, and then you know the Z, you have the population variance, you can be able to calculate the sample size. For the case of the formula for the sample size for proportions, you find that sometimes it's hard to get the sample size of the whole population. So what happens is that if you take a proportion or a subset of the population, then in that case you can be able to use the sample size of the proportion, and it enables you to come up with a conclusion of the entire population. So in this case, we are using the formula for sample size for proportions. But we're going to start with an example. Yes, of course, I echoed about this yesterday, but we can still move further. We want to look at what proportion of women had skilled birth attendance, that is the SBA, during the last delivery. It's a proportion. I mean, different. We don't know the true value of what happened, but now we are trying to see what proportion can we base on such that we are able to come up with our N, the sample size that we want to consider. So what proportion of women had skilled birth attendant during their last delivery? So this is the scale I'm having. So from 30 to 90. So assuming that the true value is 60%, we are just assuming, then by the end of the day, we are going to generalize, okay? And they vary. Maybe from the true population, there is a margin of error, or the level of precision. Here we'll have the difference of, this is 5, the difference of 10. And then in case that one, maybe it will be a difference of 20, okay? Then, but remember what we said, the smaller the level of the level of precision or the margin of error, the higher the chances of us having the true value. So assuming, and this is what I was calling the margin of error, my bars, the difference in between from the true value up, this is my true value, and then in case the estimated one here is 80. So what is the difference from this estimated value to the true value? In this case, you can look at it and it is 20, and then also on the other side it is 20. But the point is that the smaller the margin of error, or the smaller the level of precision, the more we can trust our true value. So in this particular case, if it is just 5, a minus of 5, and then a difference of what? A difference of 5, assuming I'm taking a 5%. So it's gonna be 55 and then 65. So we have a plus and then the minus. We are still looking at, the point is that the smaller the margin of error, the higher the chances for us to estimate the true value. So what point am I trying to drive at home? In case the red P is my true value, okay? But in my conclusion, I need to also put into consideration the issue of an error, maybe that I might face during the sampling. So if I've got if the true value is capital P, that is red, and the estimated value, for example, my small p is below by 5, or it's above by 5, assuming that my estimated B is the blue P, the small p, and then this difference in between, that D, it's what I'm referring to as the margin of error. So you can state it mathematically that if we want a sample size to ensure that we can estimate a value, say P, from my sample, okay? That is the estimate that I want to make with a which corresponds to the population parameter P, my true value. So since we cannot guarantee that P will be that the estimated value will be our true P, so we allow a certain level of error. So, but this error, it has to be limited to a certain extent. So in this particular case, it is what I'm referring to as D. So I don't want to go into a lot of maths. We can just express it in this particular term, that my estimated value, when you get the estimated value minus the true value, which is my capital P. So always this value will lie between a plus or minus D. My D is the margin of error or the allowable error that I've considered. So in other words, this is the difference between the estimated P and then the true P, but that is not greater than plus or minus D. So in other words, we are looking at how much error or allowable error can we consider in case we are looking at the difference between the estimated value from the true value. So in other words, sometimes it's also important that we want to attach the level of confidence or the limit that I already talked about, which is 95%. And we know that from what we know that most of the time it's 1 minus alpha, that is the probability of 1 minus alpha, it is always equal to 95%. And it's always a common practice that we use our confidence limit at say 95%. And in that case, our error, the alpha, the level of significance will be 5%. Okay, I don't want to go into this. It's the same thing that I'm explaining, only that it is giving the, it's just how to state it differently. So from the basic formula in case of confidence interval, it's always usually the estimate plus or minus. If you remember yesterday, we considered all this part as our margin of error. We've got an estimate plus or minus the margin of error, whereby my SE is the standard error of the estimate. So since my D is the margin of error, so I can get the whole of this particular portion, my D, to be equal to Z1 minus alpha over 2, then times the standard error. Remember, we are considering a proportion of a sample. So in this particular case, I'll use P, a proportion. So, so I'll have P, then 1 minus P, probability of success, and then probability of failure. I divide by my N, which is the sample size. So what we are going to do from this particular expression, all we need to do is to make N the subject. If we have our estimate, we can read the D, we can read the Z, and then substitute in the D, we are able to calculate our sample size. This is just calculations. You can neglect that, but the main point is the one here. By the end of the day, in case you do manipulation, your N, the sample size, will be equal to this. This is the sample size in case you're calculating the proportion of means, what we usually use. Okay, my N is the sample size, the Z at 95%. You can pick it from literature. It is always 1.96, my P are the proportions, and then my D is the margin of error. Of course, as you read in various literature, like I mentioned earlier, you can take D from 0. plus or minus 0.5 and below. In case you're using published tables, they'll give you the ranges that in case you're considering your level of precision or the degree of margin at 3%, what will be your D, or what will be, in case of 5, in case you're considering 5%, what will be your D, among others. Okay, this is just an example. It's just a substitution from the previous formula, whereby I'm putting in my Z, the 1.96 squared, then the proportion of success, 0.4, then the other one is 1 minus P, which is 0.6. So when you feed into everything, here my D, well, they use 0.1. So, and by the end of the day, the N that is suitable will be 93 observation or patients, or depending on the purpose of your study and the N that you want. Okay, then also note that the sample size requirement is highest, okay, when P is equal to 0.5. Still, that is the degree of variability that we talked about. And it's a common practice to take P as 0.5 as our maximum variability. So since when there is no information is available about the P for a conservative estimation of a sample size. So if we are to consider P as 0.5, and then here we consider the cutoff, that the margin, the margin of error at 0.05, which is 5%. And then, so considering our level of significance at 0.05, we are able to get our Z. So in this particular case, most of the time, your maximum number, your N, the sample size will come up with 385. Just for an optimum or for conveniences, somebody can decide to come up with an approximate of 400 as the sample size. All right. Now, as we continue, I want us to discuss, we've looked at if we want to determine the sample size. I've already discussed about whatever that is on this slide. You have to consider the level of significance. That is our alpha, which is 0.05 in case we are trying to determine the Z. Okay, then the desired power, I'm going to talk more about that. That is the 1 minus beta or the type 2 error. And then you can also pick justification from previous data. I've already mentioned about previous work in literature. You can review records, you can use published data, and so on. It is important to note that, okay, in case you increase your margin of error, increasing the margin of error would reduce the sample size. So it is just a trade-off. In case you increase the margin of error, most of the time, you'll be reducing your sample size, because remember, it is in the denominator, all right? And if you reduce the margin of error, you will be increasing your sample size. So that is the trick behind. In case you want to have a larger sample size, then it implies that you need to reduce your margin of error. And if you want a small sample size, you can have how do you determine the sample size without a population size? Like I mentioned earlier, when you look at, for example, when you look at this particular example that I've given you out, all right? If we are to use the formula for calculating the sample size with proportion, yes, like I said, the population could be very big, but you can opt to take a fraction or the proportion of the population. The sample that you pick, when you use a proportion, the mean proportion, you can use the mean proportion to support you to calculate the sample size. It doesn't necessarily mean that you need to know the capital N. When you know the capital N, well and good, that will be very okay. You can use systematic sampling. And in that case, you have to know what small n, what n do you want to consider for your study, all right? But in this particular case, if you use the proportion, the sample proportion to the mean, you can be able to calculate the sample size without necessarily having the population size. All right. Yes, I think I've mentioned about this. It is in case sometimes you might look, depending on depending on the purpose of your study and the allowable error that you want. Are you going to consider a very small? Are you considering is the population you want to consider very small, So in that particular case, if it is very small, then it implies that you have to increase your margin of error because the population you're dealing with is very small. But in case it is very big, you want to have a large sample size, then it implies that you have to reduce your margin of error. Okay, this slide, it shows various formulas and the basic rules that you can consider in case you want to, if you want to make comparisons between the means, how the formula for the different sample sizes. So still, but I'm not going to go through each of them. It is just, you can still have a look at them. What happens in case of one sample, in case of two sample, etc. I've discussed about these particular terms that we need, the p-value, I've talked about it, the probability, whereby the null hypothesis is true. And then we have the level of significance, that is our alpha. Most of the time, the cutoff is 5%. And then the power of the test, that is the 1 minus beta, the type 2 error, whereby you collect, reject the null hypothesis when there is indeed a real difference or an association. In other words, you want to check if the probability of an effect is there in the sample that you want to take. Okay, there's also what we have, as we move on to the practice in R, we have what we call an effect size. Okay, maybe in case in case I go back briefly here, some of the statistical terms we are talking about that we need to include the p-value, the level of significance, the power of the test, the 1 minus beta. Here, also in this particular case, most of the literature typically sets the power of the test at 80%, the probability of finding an effect, if in case the effect is there, or the sample that you choose will enable you to say that the results that you're going to get at the end of the day, they provide you the right recommendations. And then also we need to know about the effect size. Just sometimes, most of the time, it's for clinical importance. What will be the effect size that you're going to pick? Will it enable you to get the objectives that you set earlier? So mathematically, for us to get the effect size, in case of a 1 sample test or a 2 sample test, most of the time, in case you've looked at a t-test, it's the difference between the mean for group 1 and then the mean for group 2. My mu1 is mean for group 1. My mu2 is the mean for group 2. Then I divide with the common standard deviation, because I know that with sigma square, that is the common error variance. And when I take the square root, I'll get a standard deviation. So the difference between the two means, most of the time we refer to it as delta between between group 1 and group 2. So if you get that particular difference and you divide it with the standard error, then that gives you the effective size. Also, as you move on to, like I said, a lot within the published methods on how to calculate the sample size. For example, if you check in Cohen, all right, suggests that if you're considering a small sample size, then you can use your effective size as 0.2. If it's a medium size, you can use your effective size as 0.5. And in case if it's a larger size, you can use 0.8 as your effective size. Because by the end of the day, when these people were designing out or were coming up with these formulas, some primary studies were first done to see that they were proportional or similar to other studies. All right, so this is important. It's an element that we are going to meet when we get to R, within the commands that we're going to see, whereby you need to state your effective size that you want to consider. It will say this effective size still varies from the test that you want to see, that you want to do. Is it a chi-square? Is it an Anova? Are they linear models? etc. We are going to look at that. Okay, I've talked about the power estimate. Now, yes, I've talked about the power estimation, which is equal to 1 minus beta. Our beta is the type 2 error. So the point is that we have three things. We have the sample size. Now we know we have the effective size, we have the significance level, and then the power. However, in case you have the effective size, okay, I've told you how do you determine the effective size, taking the difference between the means you divide by the standard deviation. Now, and in case you have the power, like I mentioned, most of the time our power is the cut, it is given as 0.8 or 80%. All right, the probability of finding an in case the effect is there. If you have this particular three, you are in position to determine the sample size. If you have the effective size, you have your alpha, that is the significance level, and you have your power, you are able to determine the effective size. However, on the other side of the coin, in case you have the sample size and you have the effective size, also the significance level, you can be able to determine the power in case you want to directly suit it in your study. What do I mean? When it comes to power estimation, it allows us to determine the sample size required to detect an effect of a given size. So, and we know that the power of a test is just the probability of rejecting the null hypothesis if it is what? If it is false. With as we move on, still more details will be given when it comes to hypothesis, but we know that it's always equal to 1 minus the beta, which beta is the type 2 error. All right, so now that is the theory part of it. I want us to move to R and see how can we use R to calculate the sample, size. Okay, before we move to R, there are some questions that explain the relationship between a target population, a sample size, and then a sampling procedure. Now, we looked at, in the start, we say that what is a population? Okay, a population consists of if you're an instructor. So in that particular case, your target population will be students, all students within the class. That is the population you're considering. If you're looking at it in terms of, if you're going maybe to consider, what example can I take? Maybe the performance of a certain variety, and you want to get the information from farmers, okay? So in that particular case, you will be considering farmers. In other words, what is your interest? Which people are you, what people are you looking at to be part of your study, or to be the ones that will be able to enable you to ensure that you derive the interest that you want to get by the end of that day. That is the target population. Like I say, they could be students. You can consider, for example, maybe you want to look at the performance within the schools at country level. So in that case, it will be the schools that will be the population you want to consider. Population does not necessarily mean the individuals, but it could be maybe you want to look at cars, how a certain type of fuel is affecting cars and so on. All right, and then with the target population, it is specific to the study that you're looking at, because different studies have got different population. Maybe in case somebody could be looking at students, others could be looking at farmers. Specifically, what population are you going to look at? And then, because sometimes I talked about if you want to check the performance of the students, and the students is your target population. In case, for example, your class could be having, let me say, like 500 students, and you feel that is your capital N. okay? But these numbers are very big. So what you do, you take a subset. For example, instead of taking the whole 500, you can decide to choose maybe 100 out of the 500 students. So it implies that this 100, it is a subset of the population, the target population, and it's what I call the sample or the sample size. So it is just the sample is a subset of the targeted population, and we usually pick a sample such that by the end of the day we are able to make an inference or conclusion about the entire population. I mentioned about the various reasons why sometimes we go ahead to sample, especially when it comes to the issue of cost and time. So that is that. And then when it comes to a sampling procedure, we've looked at, when I discussed about issues to do with the sampling approaches, for example, the simple random sampling, you can talk about systematic sampling, and then cluster sampling, and or stratified sampling. All those are sampling procedures that can use and they enable you to arrive to a specific end that you want. For example, I talked about systematic sampling, whereby there are three issues that are involved. This time around with systematic sampling, you know your capital N. We talked about the students in class. Maybe you want to test their performance. In case your capital N, for example, it is 100. Okay, if they are 100, and in your sample, you only want to include, for example, 10 students. Okay, so what is important in this particular case, the way you hear the word systematic, so you can consider how do you get the systematic sampling interval. So you're going to get the total N, that is your population size, you divide by the small n. The moment you divide, you're going to come up with 10. So it implies that between 1 and 10, you're going to use simple random sampling or just a random process. You can start with any number. Let's assume maybe you pick 2 as your first starting point or as the first number that you've selected. So it implies that now the 10, this particular 10 that you got, the division that you got, what I'm calling the systematic sampling interval. So it implies that from the person that you've randomly selected, so you'll be picking every 10th. You'll count, and the moment you get to the 10th person, that person is included in your sample size. You count in case you picked number 2, so you'll count and you'll count the persons in the middle. So when you get to the 10th person, that person will be included in your sample. So after that, you count again. If you get the 10th person, that person will be included to your sample until when you get the n, which is equal to 10. The moment you get to 10, you stop. Those are the people or the respondents that will be within your sample size or the selected respondents. So that's what I mean by that is what is meant by the systematic sampling approach. So I've talked about the sampling procedures, we've discussed about them. The systematic sampling interval, what happens, the way you hear the word interval, you sample after every nth or after a certain number that you've chosen. How do you get it? You get the population size. For example, if it's defined, you know the n in your class, the students that you have, and then what size do you want to include in your sample? In case you only want, for example, 10 students, then when you divide by 100, that 10 you get, it will be your systematic sampling interval. Okay, in case your n, for example, let's assume it is 50, all right? And you only want to pick, if your capital N is 50 and you only want to pick only 5 students. So for you to get your systematic sampling interval, it will be 50 divided by 5, which will give you 10 again. So in this case, between 1 and 5, you'll choose the first person you're going to start with, or the first students that you're going to consider. And then thereafter, you'll count until you, from one that you've chosen, that will be the first unit or the first element or the first person there that you're considering in your sample size. And then now you start counting up to every 10th person. So the moment you count up to the every 10th person, for example, maybe you could be using a registrar, or you're using an attendance list as your sampling frame. So all those people that will fall in the position of the 10th, they are the ones that you'll consider, they are the ones that you'll put within your sample, and they will constitute your sample size. Okay, then the difference, what is snowballing? Snowballing, it is a technique of a non-probability sampling procedure. When it comes to snowballing, like I mentioned earlier, it is usually used when it comes to hidden populations or sensitive populations. The example that I gave, for example, the drug addicts. Sometimes you might want to do a study using drug addicts. So if the drug addicts, now in this case, they will be your target population. But you know, you're trying to, it is not easy to get them. And what you can do, maybe they can give you an advice that in case you get they are mostly stationed in a certain place. But in case you get their leader will be able to tell you that, will be able to take you to other persons that do take the drug as him or her. So in that particular case, that is the snowballing. It is like syndicate, okay? You start with one person, then this one person leads you to the other person that you get, you can also ask him, and then also leads you to another person. Then when you get to the fourth person leads you to the other. So until when you get this the sample that you think that it is suitable for your study. And it's mostly used in qualitative studies. Somebody asked that earlier. So that is snowballing. Another example that I gave, in case you're conducting a study about prostitutes, it is also a hidden population, because you're not going to go somewhere and then somebody comes out and say, you know, me, I'm a prostitute. It is also an hidden population. But many studies in countries are carried on prostitutes, and they come up to give their ideas and perception about things, on how their business is. But still, since you do not know since it's not an open population, maybe, for example, I'll give an example of taxi drivers, where you can get them in the different parks where they usually reside to pick passengers. So you can get, they are usually contact persons on how you can get to these particular people. So in case you get their leader, they also have associations, and they have got leaders. So in case you get maybe a leading person in this association, or a contact person, then it implies that you only start with one person, and then this person leads you to other people that fall in the same category. Then the other one, that which formula is the best if the population is divided into known and then unknown. In case when it comes to the formula that you want to use, like I said, there are various formulas, but it all goes back to what is the purpose or the objective of your study. It will be the one that will really direct you to say that this is the formula that best suits for me for this kind of study, or I'll use something different. But also, for you to come to the best formula, it goes back on what sampling approach did you use? It is also important. Then it will be able to lead you to the best formula that you want to use. All right. Now, so let me ask in the chat, can I move on? Are we still on the same page? Okay. If you have questions, kindly post them in the Q&A, because if you post them in the general chat, they disappear very fast. Post them in the Q&A. Now we are going to move to R and see how do we determine the sample size. But remember, as we said earlier, R has got various packages. Okay. Okay. Somebody's asking about the power estimation. When we're starting on the discussion, there are some things that you're not going to miss out in case you're calculating. When you're calculating the sample size, as far as the power estimation is concerned, power is 1 minus beta. We know that beta is type 2 error. In other words, you fail to reject the null hypothesis. Failure to reject the null hypothesis when it is what? When it is false. Okay, so in that particular case, what we are trying to find is that the probability of checking if an effect is there within the populations, the sample size that we have determined. So the point is that it just allows us to determine the sample size that is required to detect an effect. And most of the time, by default, we estimate our power estimate P is always equal to 80%. Okay, though that is from the literature, though it can still keep on changing. So it is just the probability of rejecting the null hypothesis if it is what? If it's false. And I mentioned that when you're looking at these 4 quantities that I stated here, if you have, for example, the sample size, the effect size, and the significance level, when we move to R, you can be automatically, if you put in the command, it will give you the power estimate. And also, in case you're having the effect size and the significance level, as well as the power, you'll be able to calculate the sample size. All right. Okay. So like I mentioned earlier, these things already, I mean, they do exist in literature. In case you're considering your power as 80%, these are just the values for a 2-sided test and then the 1-sided test. So for a 2-sided test, it will be 0.8. You can consider the power as your 95%. It could be 90%, 95, or 99. And then when it comes to alpha, our level of significance, it could be at 1%, 5%, or 10%. But we are going to see in R, you can automatically, they are computed. So we'll use what the PWR package. Within the PWR package, it's the one that enables us to calculate the sample size. And within that particular package, if you look at my left-hand side here, we have, like I say, the PW package. It's the one that has got all the functions for power analysis, the PW. So you can use all these in case you want to the conventional effect size. You can click here. I'm going to do everything in R, and then we'll see that. In case you want to find the power calculation for 2 proportions, same sizes. This is the kind of test that you're going to use. What about in case it's an Anova? Okay, a one-way analysis of variancy. We have the pw.anova.test and so on. It all goes back what is the purpose of your study. In case you want to do a t-test on means, for example, if it's a 1 sample or 2 samples or paired sample, this is the test that we shall use, pw.t.test, etc. Okay, among others. Now let's go to R. I'm going to stop sharing this, and then we move to R and see how do we calculate N in case you have power, or what? In case you have power, how do you get the sample size? All right. There's a please send materials also to email. Okay, so let me ask in the chat, can we move on to practice? Can we get to R? Okay, now go in the folder of dev 4 and open sample size underscore power R script. If you're ready to go in dev 4 material and open sample size underscore power dot R. Your prof. Okay, let me ask in the chat. Let me ask in the chat. Somebody is asking about what is meant by type 1 error. Somebody to tell us, just type in the chat, then I read. Type 1 error. When is a type 1 error committed? Or what does it mean? Anyone to share answers with me? Type in the chat. Anyone who knows what it means? Stefan has typed alpha, the level of significance. Thank you. Somebody else? Rejecting a true null hypothesis, correct? When you reject the null hypothesis, when it is true, Sam, thank you. That is right. Means rejecting the null hypothesis when it is actually true. When you reject, okay, probability to reject H naught when it is true, false positives, null hypothesis when it is true, the risk of rejecting, then when we reject the null hypothesis when it is true. All your answers are right. So in case that is the probability over the probability that the null hypothesis is true. That is type 1 error. Probability of rejecting the null hypothesis when it's true. Yes, great. Or you can call it the significance label. All right. The other one is what? Prof. Okay, now let's move on to type 2. Type 2 error. The meaning, because some people are still asking what. So now we are done with a type 1 error. We are saying that's the probability of rejecting the null, the probability that the null hypothesis is true. Okay, now let's move on to the type 2. I'm waiting for your answers. When we fail to reject the null, failing to reject the fourth null hypothesis. That is Haley. Thank you. The power of the test. Great, that's beta. More answers. Accepting H naught when it is false. That is also correct. Not rejecting the null hypothesis when it is false. Accepting a wrong hypothesis. Accepting a false null hypothesis. Okay, great. Thank you. Failure to reject H naught when it is false. That is right as well. Okay, Levy, Washington, thank you. Beta 80, accepting fourth hypothesis. All right, I think now we are good to go. You've gotten the difference between the two, the type 1 error and then the 2 type error. Accepting null hypothesis when it is false, that is committing type 2 error. Wonderful. So can we proceed to R? Type yes or no? Can we proceed to R? People are still sending in more answers. Thank you so much. I've shared my R studio. I don't know whether it's what you're viewing. Are you seeing my R studio? Is it what you're saying? Okay, great. So as we move on, kindly ensure that maybe as you opened the sample size power.r script, sometimes automatically R will tell you that within this particular script, you need to install the PW package in case you don't have it there. So in case you get such prompts, all you need to do is to click on install, and then you move on and you wait for it to install, and Are you sure? Kindly confirm to me if you've got the script. Yeah, Lily is saying that it has it, but some people are saying that it doesn't. Now I think it's some people do not know how to pick the script from there. What we are doing, we keep updating that link every day as per the sample size _R. But some are saying that it has. Did you share different links? Is it okay if you can share it in the chat as well? If it's you've shared. Okay. For now, open the sample size _par.r script. Please check properly that script is there, because we keep updating the same link. So it puzzles me if some people say the script is there and then others say it is not there, because it's the same link. We just update the material. I want to zoom in. Okay. So, okay, if you've opened your sample size _par script R, is what we are going to use. In this particular case, don't worry, we are not going to do data importation. No, it is not there. We are going to just proceed. Like I wrote here, I said that there are two techniques on how you can calculate your sample size in R. One way we are going to do it in case without installing any package, the commands are there, and then when using the PWR command, okay? Most of the time, in case if you're trying to find the sample size, you're finding that you can be able to calculate the sample size if the power is given. Remember, we've talked about the power estimation. So in this, we are going to use this particular command, power.t.test. But let us first get to know how does this function work, because it will make more sense if you're understanding what exactly we are doing. So assuming that we are looking at, you're comparing two groups, okay? I zoom in. Okay. Now, on your computers, let's first understand. You can either write help, in bracket, you put what you want help on. In this case, we're going to use power.t.test. So in case in R, remember we said these commands are inbuilt there, but for you to use them correctly, you need to know how do you use the different arguments. So in case I run this line, okay, I'm going to come back to my help window and get to know what exactly the command is all about. So they give you the description that it's compute the power of 1 or 2 sample t-tests or determine the parameters to obtain a target power. All right, so this is what we are given. We are given the usage. So we have first the power.t.test, and then inside here, we've got various arguments. We have our n, that is the sample size, and they have said it's equal to null. So most of this, in case we want to calculate our n, so we'll not put it there, but R will be able to compute to us. We have delta. Remember what delta is? It's the difference between the means mu1 and mu2. In case of a one sample test, we get the sample estimate minus the estimated. Okay, my x bar minus mu naught. Then by default, they are giving you that the standard error is 1, the significance level is 0.05, and then the power, they have put it as null, but you can indicate it. Then we have the type. Are you going to consider a 2 sample? Is it a 1 sample or paired? It depends. And then you can pick on the type that you want. When it comes to the hypothesis, it will always pick for you. It will give you the alternative and so on. And when you move further, when you move down here about the different arguments, still R explains to you what the different inputs within the command refer to. For example, N means the number of observation per group. So it implies that in case you're considering a 1 sample t-test, it will tell you that, well, basing on the delta, basing on the power, this is the sample size that you need to use. Then I mentioned about delta, the true difference in means, the standard deviation. By default, it gives you 1. So we need to put that. Then the sig dot level, this is a significant level, or the type 1 error probability. Then the power, this is the power of test, which is always 1 minus the type 2 error. You have to indicate the type in case you have it, the alternative, and so on. So what is interesting in R, apart from showing you the command, when you read further, even the guide to give you some of the authors you can refer to, but even the examples that can support you. You can first test these particular examples, and then later you refer to it direct to your work. All right. So in this particular case, they are showing you that, okay, with the power.t test, in this case, you have n as 20, and then there's delta as 1. So looking at this particular example, number 1, it implies that what R will do, given your sample size as 20 and the difference between means as 1, it will give you the power of the test. Or in case you've got, you have your power as 0.90 and delta as 1, this will return to you the kind of n, or the sample size you are likely to use in your study. At the same time, by default, you can be able to indicate, we are going to move on to the types and so on, whether the alternative you've indicated a one-sided or a two-sided and so on. So this is the relevancy of using the help command just to support you, to ensure that what you're doing is in line with what the package wants. All right, now let's move on. Okay, let me ask in the chat, have you understood what the power.t.test mean? Okay, all right. Now let's check its application. Good. Okay, let's check the application. Now that we know what our power.t.test mean, like I said, with this one, you don't need any package, okay? You don't need any package. So in case you're using the power.t.test, we said one of the arguments that you need to put in this particular case, remember, it is delta, okay? In case the difference between the means, the two means is 0.2, that is mu1 minus mu2. Let's assume it is 0.2, and then the standard deviation is 0.5. And we set by default our power to be 0.8. The other thing that you have to note in mind that this command by default, it will consider a two sample test. in case you just type it like this, okay? By default, it will give you the type of a two sample test. Or in case you want to be more clear, you can go ahead and include this. You can go ahead and also include the type and tell R that it's gonna be a two sample. But by the end of the day, this and this command, they give you similar result. So in case you've tried to feed in what is required, if you click run, when you click run and you come to your console, when you come to your console, these are the results you get. R is telling you that it's a two sample t-test power calculation. And you stated that the difference between the means is the delta is 0.2, the standard deviation as 0.5. Automatically, R sets the significance level to 0.05. And then you set your power as 0.8. But in case you want to change your power to something else, you can put it to 0.9 etc. But most of the time, the default value is 0.8. So what happened is that basing on what you're considering, and the alternative is a two-sided test. So R is telling you in this particular case, if you are considering your power as 0.8 and your level of significance as 0.05, then it implies that your N is supposed to be 99, or you can approximate it to 100, that N is the number in each group. So R automatically tells you the size of N that you are going to consider in your study. So in this particular case, in each group, you're going to consider okay. It was just a short break. Let's continue. Okay. That's what I put. All right. So when you look at this other command, I'm not going to run the second one because I've already mentioned we're going to come up with similar result. So let's look at a case when we are considering only a one sample. So I've put my power as 0.9, my delta as 0.3, my standard deviation as 0.28. All right, and I'm telling R that it's a one sample, okay? If I run this line and I come and I check in my console, it will tell me it's a one sample T power calculation. So basing on what you want to consider the level of significance as 0.05, your your delta is 0.3 and the power at 0.9, then your n, the appropriate n, will be 11. All right, like I said, you can play around with these numbers. It always depends why in your study, why have you decided to take your delta as 0.3? Of course, I mean, we know how to get the delta. It emanates from our study. Then we are able to calculate. If you have the power, you have the delta, it will give you the n. If you have n and you have the rest, it will give you the power. All right, so in case we move, I continue. Yes, this is also another way. This time around, what I did, I changed my power to 0.9, the delta to 0.3, and my standard deviation to 0.28. All right, and it is also a type 2. So in case you run that, R will be able to tell you the appropriate sample that you'll need in each particular group. So if it's a 2 sample, that in each group you'll consider 19. So for you to get, if you're picking 19 and then 19, to get the total the total n that you're going to use, it will be 19 plus 19. It is the sample size that you'll consider, and having equal size in each group. Okay, what about in case of proportion? Still, when it comes to this particular command, you can type it in R and see the different arguments that you can look at. For example, if you're seeing my screen, there is n, which is equal to null, p1, p2, all those you can feed in. You can feed in the power. We are given the alternative, which you can choose from. And in this case, still, I've taken if you feed in the arguments, assuming that I'm taking the first proportion, the mean for the first proportion at 60%, which is 0.6. And then the second one at 0.5, that is if I choose 5%. And then my power as 0.8. So if I run that, you'll come to R, and it will tell you that this time around, it is a 2-sample comparison of proportions power calculation, and your n is equal to 387. This 387 as your sample size will apply if in the first sample you chose a 0.66 that is 60%, and then in the second one it was 0.5, the significance level 0.05, and then the power as 0.8. So implying that n is the number in each group. So you'll have to have this, and then you multiply it by 2 to get the n that the total n, the total sample size that you're going to use. So from each group, you'll be picking 387, at least 387 subjects from each group. That is a technique in case you're not using any particular package. However, still in R, there is an inbuilt package that I talked about, PWR. If you've not installed it yet, please do. Otherwise, you're going to get an error. After installing, all you need is to run the library. You type library PWR. So with that, like what I showed you in the PowerPoints, this library has a lot of functions, many inbuilt functions inbuilt there that can be applied in case you want to calculate different sample sizes. Now, under the PW package, we have this particular test. This is the test that we're going to use, PWR. Initially, it was power written in full. Okay, now this one is just PWR.t.test. Okay, we can still find out more with R. Let's check what I mean, in case we want to use that particular command, what exactly are we supposed to do? Let me run it. Okay, in case you run, you come to your help window and see what has been given out. So here, we are having a description that compute power of tests or determine parameters to obtain the target power. All right, when you move further, you see the usage. Still like in the first one, this time around it's pwr.t.test. You have N, which is our sample size. You have D, you have the significance level, which is at 0.05. You have the power, they have stated it as null, so you can state it. You have the type and then the alternative. All right, so again, among the arguments, they are saying that what is N? N, these are the number of observations per sample, depending whether it is 1 or 2 or paired. All right. Now, within this package, we have D. D means the effective size. Okay. This is according to Cohen's D, which looks at the difference between the means divided by the pool standard deviation. I've already explained about that. And then the rest of the information is the same. What is being included in this one, it is just the effective size. Then we have the power, we have the type, and as you move further, you see the author, the reference. This is a common name when it comes to statistical power analysis, especially in sample surveys. He developed a lot of different ways, formulas on how you can calculate sample size. Even when you move further, there are examples, like I said, in case you're looking at a one sample and you have the power, or so in case you want to calculate the power, this is the formula. They are giving you an example that you can refer to. We have the pw.t.test. We are given D. Remember, our D is the effective size. If you remember very well, it's a difference between the means divided by the standard error, or it is the delta over sigma, if you remember very well. And then in case I consider my N as 60 and my significance level as 0.10, like I said, you can play around with these particular figures and you consider only a one type sample. So you can be able to find what power is that. And this exercise is gotten from Cohen 1988, as the way it is stated here. And you can look further and see other examples that are being given. And then after understanding how these examples are, then you can now apply direct to your work. All right, now let's move on. Let's go back to R and see. Okay, I've talked about, I'm going to use this particular command. I need to know what it does. I've seen the different arguments. There is delta. Actually, there is D. My D is the effective size, the effect size. And we said that the effect size is the difference between the means are over the pooled standard error. So in this case, so if my delta is 10, that is the difference in mean. If I'm considering a one sample test, so it will be the sample mean minus the hypothesized mean. And then I've got the sigma, which is 20. This is my standard error of the mean. So for me to get the effective size, I'll need to get this. I divide by that to give me the effective size. Okay. And then all I need to do is to come and feed into my formula, my command, where there is D. This is my effect size according to the formula that we've just seen. I'm taking the level of significance to 0.05 and then power as 0.9. You can change it to the default one, which is 0.8 or 80%. And then the type is the type is one sample. In case you don't include the type, by default, it will give you a 2 sample. So let's run this. So I have that, I run, I'm telling R that my D, that my delta is 10, my sigma is 20, okay? You can check in your environment that what you're running is okay. And then, so my size effect R, or call it D, is delta over sigma. Because this is already recorded, then I just need to run that line. And then I come and I run my power WT test to see what n do I need. So when you come here, it's a one sample T power test. If the effective size is 0.5, this is my D, and the level of significance is taken at 5%, and the power is 0.9, then your N will be 44. That is, this will be the recommended 44. The sample size that you'll pick. When you move further, in case you're considering a 2-sample test, it's the same thing that I'm using. I'm still using the same delta, the same sigma, and then, but what is changing here now? I changed my significance level to 1%. This is to 0.1%, and then my power to 0.8. And I've commanded R that my type is a 2-sample. So all I need is to run these lines, and I get to know what will be my what will be my N. So when you look at the results in the R console, R is telling me that basing that it's a 2-sample t-test per calculation, that basing the effective size again as of 0.5. This time around, if you consider your level of significance, it will be 0.1, sorry. Remember, we said the level of significance varies on, in case you're dealing with a sensitive population. For example, in the medical field, sometimes they opt for 0.1 level of significance. If your power is 0.8, then your N, you have to consider your N as 50 from each group. N is number in each in each group. Now, when it comes to delta, I said, is delta assumed or calculated? Delta can be calculated. Remember what we said about delta is the difference between what? Between the means. If you're considering a 2-sample test, then it implies that you're going to get the average or the mean from each group. All right, and then you subtract. Delta is a difference between the two. You can calculate it. And then the moment you have your delta, if you divide by standard deviation, you get the effective size. And this one, R does it automatically. Okay, and R to give us the, is it? Yes, I mean, all these, whatever sample size we are having in R, in the background, it is developed on Cohen's formulas. The person, the author was talking about who was carrying out various studies on how to come up with an appropriate sample size. So all these formulas are based on that author. So what is the range of delta? Understand what delta is, and then the ranges shouldn't be a problem. What is the difference? There's nothing like range. It's just the difference of the means between the two groups. In case you're considering a 1-sample, you get what you do, you get the sample mean of the sample, then you minus it with the hypothesized one or the estimated mean. Okay, and in that particular case, you'll be getting delta. So So the difference between power and n, power, we say that for the case of the power, like I mentioned earlier, in this particular case, it's 1 minus beta, okay? Which beta is the type 2 error. And all these are inbuilt in R. All you need to do is use the appropriate command, and then it will automatically give you the results. And by default, always our power is 80%, but you can change it in case you have your other reasons that you can refer to. Then n is the sample size. Our small n is the sample size. In case of a 2 sample test, there is a note down that n is the number in each group. So in other words, in case your n is 50, like the way we are having here, it implies that in each group, you're supposed to consider 50 observations or 50 elements. In case you're considering patients, it implies that you're going to consider 50 patients in each sample, maybe in case you want to get their blood pressure or taking any measurement that you want. So you'll have to pick 50 observations, or call it elements, or call it units from each group. Why are you varying delta, SD, and power in R? I think all that is answered from what I've just explained. Let me ask in the chat. At what time we have a rest? I hear from you. Okay. We also have a power prop test. I've done that. And then maybe the last bit in the case of the practicals, in case you know the sample size, you can calculate the power. In this one, I've indicated my n, I've indicated the delta, the standard deviation, and I've also I've put the type as a 2 sample. So in case I run this particular command here, it is telling me that now the power will be 39%, depending on the size of n that I've put. But remember, you can still play around with the n that you want to consider. So the power of the study is 39% to detect the difference in the means of 0.3. So that is within R. And of course, in case you want to learn more packages within the PRW, there are very many. So you can still dive into them and get to know. And what about in case of a chi-square test, if you want an Anova, all these things are within the PowerPoints, but you can do that further. Okay, thank you. Now, Pro, that marks it. Okay, now that marks the part on how to calculate a sample size or how you can get power in R. Now, there is another bit on data collection that I wanted to discuss briefly, but I guess I'm seeing in the chat people are asking for a break, but also Professor Susan has to come in. So I'm just wondering how we are going to do it. Can I continue, or we first give you a break? Sarah is saying that I continue. Please, we continue. Okay. Okay, let's continue. Yeah? Just finish. Okay. I'll go with the majority. Give me only 10 to 15 minutes and I finish up my part. We take a break, and then after the break, Professor Susan will come in. Not so, if time allows. Okay, let me stop sharing that and make 15 minutes. Okay, noted. Wow. They have told me only 15 minutes. All right. Okay, no problem. Okay. Only 15 minutes. Let me share. You have the slides already. And then I finish this particular bit and we take a break. Okay, now let's move on to data collection methods and field work. I'm just going to talk about only the key things. Then other things you'll consider on your own. So here I'm going to look at what data is, the various types of data, the data collection process, and then the data collection options and field work, just briefly. And then other things will dive in as you move in your research. So as far as data is concerned, actually, if you're going to do analysis, you need data, and we know that data, these are just facts. Okay, they are organized. These are just facts that are organized for analysis. And then they also support us in case we want to come up with a certain reasoning or we want to make informed decisions. Data is derived from scientific experiments or investigations, but most of the scientific term, the commonly scientific terms that are used when it comes to data, we use facts, we use figures, and we use measurements. And on the other side of the coin, data itself does not make any sense unless you interpret it to the audience for them to come up to understand what exactly you want to mean. The different types of data, we have quantitative and then qualitative data. So in case, so data can be either in a numerical form. If data is a numerical form, that is quantitative data. If it is in a narrative form, that is qualitative data. So that is actually the main difference between quantitative and then qualitative. All the numerical data, it is quantitative in nature. And then the narrative data, it is qualitative. So we have quant and then qual. So for example, when we are looking at quantitative data, you can say amount of goods sold per day or performance of students, marks scored, all right? You can quantify. And then when it comes to the qualitative data, I'm saying that this is data that cannot be measured in amounts, but you can reflect on them. For example, you can have one is a male or the other one is a female. Or you can look at various colors and you're able to tell that this is red, blue, and yellow. Another type we can look at, we have what we call primary and secondary data. With the primary data, this is just the data collected specifically for the current purpose, especially people who are using the cross-sectional kind of survey design. Most of the time they use primary data. Okay, I mean, this is data that you tend to collect. For example, just you go to the field and then you collect different kinds of data. So that is primary data. Whereas with secondary, it's now the opposite. This is already collected data, but can be adopted in the current study. For example, in case maybe you want to do, let me say, survivor analysis, cancer survivors. You can go to the hospital, you pick that particular data. The moment it is being recorded in the various books and what, it is primary. But in case you pick it for you from the records to use it, it becomes secondary data. There are various data collection processes that we can adopt. However, all these methods the collection requires they are vigorous and they need to be systematic. So you need thorough planning, you need effective piloting, at the same time to think about the appropriate management and the analysis that you're going to use. The different data, I mentioned that we are going to look at some data collection options. Of course, the possibilities of data collections are very many. They are wide and they vary from from each study. All right. So I mean, it depends on the kind of study you're going to do. Is it a survey? Is it are you going to do an experiment? Are you going to test something, and so on? And of course, you have to weigh the pros and then the cons. Okay, I'm going to look at the common options, the data collection options. We have, for example, there's people who go to the lab, they usually do some measurements. It's like, in this particular case, you're making use of various scientific apparatuses or instruments. For example, if you want to measure rainfall, volume of water, an area, it could also be attributed the characteristics of human beings, like you want to get people in hospital getting the blood pressure, the sugar levels, and so on. Also, maybe you can use some standardized research-made scales, like you want to get somebody's feeling, perceptions, and the attitude. Apart from the measurement, others, you can do testing, okay? It's also another scientific investigation of when you want to test something in data collection. And it also still varies from study to study. And in case it's an experimental design, maybe you want to measure certain properties of objects like the specimen of chemicals, the cells, and the like. Most of the time, these people that go, for example, in agriculture, they tend to do, they use testing, for example, on different kinds of soils, okay? It can also be done on humans, like if you want to test somebody's intelligence, achievement, aptitude, and personality. I've mentioned about surveys. I don't want to talk more about them. It's like gathering many questions from an individual using a questionnaire. We've already talked about a lot about that. There are various types. They could be descriptive or explanatory. They can involve an entire population or just a sample of the population, and they can be administered in a number of ways. So there is no specific one, but it depends on the purpose of your study. So during the survey construction, it involves, how are you going to formulate your questions such that you get the right responses? You need also to jot down a background information as a form of an instruction as you're going to go to collect your data. For example, in case you're a student, it's always important to first introduce yourself before, as you're designing your questionnaire, to put a small introduction of who you are and what information do you want to collect about. You can also collect information using focus group discussions. Usually focus group discussions are grouped between 8 and 10, depending, but they're usually small groups. And the main aim, according to Kuma 2005, is to explore group perceptions, experience, and understanding with regard to a particular issue. And this now goes back to the objective of your study. Maybe you bring farmers together and you ask about their perceptions and experiences during the farming or people, customer satisfaction, and so on. You can as well move into interviewing, but remember, still when in interviewing, it involves asking a respondent a series of open-ended questions, especially when it comes to qualitative data. They use this method commonly, interviewing, and we call them in-depth interviews. So whereby that the point is that during the in-depth interviews, you, the interviewer, you need to be composed enough, and you're supposed to give the person or the interviewee time such that this person is able to tell you various stories on what exactly you're asking about. So the interviews could be formal to informal, structured or to unstructured. At the same time, it could be one-on-one or it involves groups, okay? When conducting your interview, you'll need to question, prompt, at the same time you need to probe. But at the same time, you need to actively listen and make sense of what is being said. Otherwise, you might miss out the overall objective and miss out the information that you exactly want when you went for an interview. So you need to really be sober enough. Some people do observations, and this one is also a tedious process because you have to observe and then get to know how do people behave, such that you're able to code down the right answers or the responses that you were observing. So observation, this kind of type ranges from non-participant to participant, candid or covert, and also from structured to unstructured. I'm not going to go into all the details, but you can go in your own free time, you can read through them. Then we have experimentation, especially people doing experimental design. Like yesterday, they talked about randomized trial, the CRDBs and so on. So in this particular case, in case you want to explore the causal and the effective relationship by manipulating how the independent variables have influenced the dependent variable. All right, so then the last bit is some field work. So in this particular case, you imagine that maybe what exactly do you want to do in case you're going to the field? So before going to the field, you need to prepare yourself, okay? You would have to prepare yourself very well. And you also need to know at the back of your mind, what kind of information do you want to get there? Then so in that particular case, what could be your structure of research? How can you structure your research such that it entails on the kind of field work that you're going to embark on? In case it is a survey, are the tools already in place before you go to the field? And then still, as you're preparing for your field work, things that you have to keep in mind, issues to do with funding, healthy precautions. These days there is COVID, so how are you going to face the field, the language, maybe the regions you're going to consider during your field work. You do not know the language they're speaking, but how are you going to go about that? So you need to have prior information, your personal affairs, the authorizations. Has it been permitted by the for example, different institutions have got different authorization they can offer you in case the authorization has been made. And then also, is the research, is it specific to a particular topic or if it's for a group? And also, what you would do in case you get to the field or in case you get there, things you have to note again is you have to establish a rapport. You have to learn the language, or you can move with a research assistance that will enable you to support during the data collection or help you to interpret what the respondents are saying. You have to take notes or to take photographs, and also you can do case histories. You can participate as well as observe. All right, and then also, how do you structure your research, and what would you do when you got back? So what is important? Selecting a research problem. I mean, you need a problem first. If you don't have a problem, then what are you going to work on? Then you formulate a research design. We've looked at this. There's collecting data. After collecting data, you do the analysis, you interpret, and then present or disseminate your results. All right, so now I'll put a simple exercise. In case somebody will be ready tomorrow, we'll be happy to see the presentation. In this research, we can have like 2 people. Think of a topic, already the topics that you have, then tell us the objectives that you want to achieve. Then what data collection method would you anticipate to use and why? And then also think of how you can compute the necessary sample size that will enable you to achieve the stated objectives. I'm going to stop there. I'm sorry if I've been very fast, and then that will mark the end of my presentation today. Thank you very much for being a good audience. In case you still have more questions, keep posting them in the Q&A. We'll be happy to answer them. Thank you. And now we are going to take a break for 15 minutes. 10, okay, a break for 10 minutes. So what time are they coming back? It's 12:38. Okay, we are 12:49. Let's make it 12:50. Okay. Okay, now we are going to resume at 12:50 Ugandan time. So try to check if it tallies with you where you are. 12:50 it's when we are going to, Professor Susan is going to set and resume from there. All right. No, Samuel, not 12:55. It's 12:50.
Good afternoon, participants. I believe you've had a good break, and now we are changing goalposts from survey sampling to statistical models, Anova, and post-Anova analysis. Are we here? Is everybody here? Let me check in the chat before I start. Can we start? Okay. Okay. Thank you very much. The PowerPoint was sent in day 5 material. The PowerPoint was sent in day 5 material. I believe you've already downloaded, so let's start. A statistical model is a type of mathematical model that comprises of assumptions undertaken to describe the data generation process. So there are various types of models. We have models such as regression. We have analysis of variance model for experimental design. We have logistic regression, but they all depend on the type of variable. They depend on your objectives. So all those models have assumptions that help the model to be valid. So this is what a statistical model is. So the type of variable actually determines the type of analysis that you're going to conduct in your data set. So before even you go to collect data, as you write your proposal, you're able to know what type of variables you're going to collect. And by doing so, you're able to highlight or even indicate the type of variables and the type of analysis. There are two major types of variables. We have qualitative and quantitative. Under qualitative, we have categorical variables. Under quantitative, we have the discrete and continuous. Discrete variables are measured normally by counting. For example, number of people in household, number of cigarettes, number of participants, number of trees, number of birds, number of animals. That is discrete variable. Then continuous variables are obtained by measuring. For example, height, weight, all those are the different types of what? Of variables that you have to consider when selecting the type of analysis. For example, when we looked at the exploratory data analysis, we found that for continuous variables, we can use the histogram. But for discrete variables, for example, if we have number of people, if we constructed a histogram, it would just have like spikes, and you won't really have a definite distribution of the data. Or if we look at qualitative variables and we construct a histogram for number of birds, then or something like name of birds, we won't really get any information from such a diagram. So type of variable determines the type of analysis, the type of descriptive analysis, and inferential statistics. Qualitative variables describe characteristics or attributes of an individual, and these include nominal or ordinal. Nominal variables are associated with names, while ordinal variables are associated with names, but they have an ordering on them. So nominal variables, for example, gender, color, vehicle type, do not have an ordering on them, though they are also names. But ordinal variables are classified according to a natural order. For example, performance. We have excellent, very good, moderate, fair, and poor. And performance depends on a certain grade they are using to classify somebody as being excellent. When we look at taste of food or taste of anything, we will measure somebody's taste. Somebody's going to say it is very tasty, another one not tasty, moderate, fair. So all those have a natural ordering on them, and they are called ordinal variables. So a data set comprises of a response and an explanatory variable. So if we've performed an experiment, for example, we've planted corn or maize and we've applied several levels of one type of fertilizer, the yield is the response and the fertilizer becomes the explanatory variable. So as you vary the fertilizer, the yield also varies. So the response is responding to the amount of fertilizer you're adding in the field. So the response, the type of response also determines the type of response, and explanatory variable determine the type of analysis. Some people call explanatory variable independent. Others call response dependent, depending on the software you are using. Okay, so let's see how the response and explanatory variable influence the type of analysis. So in your notes, I'd not summarized the notes into a table, but here I've summarized them in the table. It's the same information. I realize that if I summarize in a table, it becomes more visible and clear. So don't think that it's new information. It's the same information, but just summarized. So if we have an explanatory variable, and it consists of continuous and maybe nominal variables, and then the response is binary. Binary means two response. For example, survive, did not survive, germinated, did not germinated. All those two examples are binary response. And the suitable model for you, if you have a continuous variable, for example, we have germinated, did not germinate, we added fertilizer, and then we have a type of bean or type of corn as part of the explanatory variables. The response is germinated or did not germinate. In that case, we are going to use a logistic regression, which accounts for the binary nature of the data. If we have continuous and with mixed variables, and the response is multinomial. Mult means many, nomio means nominal, many names. For example, if we have things like test, test is the response. So we have very good, good, moderate, fair, poor, test. And then our explanatory variable is type of food. Then we also have amount of food as part of the explanatory variable. So we have a continuous type of food is nominal, but the response here is multinomial. And in that case, we are going to use a logistic regression or log linear. Then if we have a multinomial means many nominals. So in this case, our explanatory variable is going to be many types of fertilizer being applied to corn. And we are looking at germinated, did not germinate, survive, did not survive. In that case, because our response has a binary nature, the most appropriate model would be logistic regression. Then if both of them, the response and explanatory variable, are both multinomial, so in this case, our response is, for example, religious type. How does religion influence crime? Okay, so our explanatory variable, let's say our explanatory variable is religion, and then the response is crime. They committed the crime, and then types of crime. So we have the types of crime, maybe murder, maybe anything that you know about crime. So we want to know, does religion influence crime? In that case, the best model would be a log linear model, because we are now doing our cross tabulation of the two categorical variables, and because there are many categories, the chi-square breaks down. It can no longer handle the many categories, and the best inferential statistics would be log linear model. Okay, so what if we have a multinomial explanatory variable, but our response is continuous? For example, we have growth of trees, and then we have species as our explanatory variable. So we have 4 types of species, that is many names, multinomial, but our response is growth. We want to compare growth of the different species. In that case, we are going to use an analysis of variance, because remember that in analysis of variance, we want to have a categorical explanatory variable, but a continuous response. Okay? How about if our explanatory variable is continuous and then our response is binary? In this case, we've measured amount of seeds is our explanatory variable, amount of seeds planted, and then we are looking at those that germinated and those that did not germinate, and then we also look at survival, those that survived and those that did not survive. In that case, our appropriate analysis would be a logistic regression. How about if we have a continuous response and a continuous explanatory variable? In that case, if we want to establish a relationship between 2 continuous variables, then we are going to use simple linear regression. Now, we can use simple linear regression if we have 1 explanatory variable and 1 response. How about if there are many explanatory variables and 1 response? We use multiple regression. And if there are many response and many explanatory variable, then we would go for multivariate regression. Okay, in the chart, can I continue? In the chart, can I continue? Is there anybody with a problem? Okay, thank you very much. Excellent. Okay, so let's continue. So this is a guide. When you have your data, you can look at this guide and look at how you can analyze your data afterwards. So depending on the type of variable, so when you get a data set from the field, you should be able to distinguish between the response and explanatory variable. You should be able to know the type of variable you're dealing with. Is it continuous or binary? Then when you know those, then you're able to determine which analysis you're going to perform. How about if we have a binary response, we have a continuous explanatory variable and some are nominal? Then in that case, the suitable model would be a logistic regression or log linear regression. If we have continuous explanatory variable and nominal as well, and then the response is continuous, in this case, let me give an example. For example, we want to develop allometric equations for different tree species, let's say used in agroforestry. So we have 4 species, okay? And then the response is biomass. So we are going to model biomass as a function of species, and then other variables that are continuous are going to be height and then the diameter of the trees. So in that case, we can first of all run a scatter diagram to see whether there are groups within our data. So the groups according to the species of trees. Then if we find that, then we are going to run a multiple regression with the groups, and the groups are going to be species. In this case, you will find that we are going to end up with either many models for each species, meaning they have different intercept and slopes, or we are going to end up with one model which can explain all the relationship between biomass and species. So this can be visible if we are doing regression. Okay. Now, if we have a continuous explanatory variable and nominal, but the response is ordinal. Ordinal meaning they are names but with a natural ordering on them, then that type of regression is called ordinal regression. Okay, all that is available in any package that you know. So when we are doing regression, we will see some of this. Okay, any question in the chat before I continue to something else? I've told you that I summarized the 3 PowerPoint slides into a table. As I was going through, I realized, no, I think I need that table. But if you need these ones, I will also post them and you can get the update, okay? Examples in natural resources. Prof. Olivia, yes, I will give, and I've been giving examples in natural resources, but I will give. Okay. Can you say something about discrete? No, odd ratio or odds ratio is not equal to ordinal regression. Odds ratio is an output obtained okay, I will stop here. So odds ratio, when we conduct a logistic regression, we will get odds ratio. And we'll talk about that during the regression analysis. Ordinal regression is when your response has many names, but they are ordered according to natural ordering. And then that response is a function of the explanatory variable, which are continuous. For example, if we have taste of food, and then we have things like weight of the amount of food given out, we have type of food. So type of food is nominal, it's an explanatory variable. Weight of the food is explanatory, and we want to find out whether there's a relationship between weight of food and type of food and our taste of food. That's when we can use ordinal regression. Okay, I am going to post this table, yes, and I have not shared it with my colleagues yet, so they can't even post it as well. But as soon as we finish, I'll do the posting. I can even post it in the chat later on. So let's continue, but I'm going to post. But you still have the same notes, but I just organized them. Okay, so let's look at analysis of variance. So analysis of variance, abbreviated as Anova, it is an overall test to find out whether between more than two groups there are differences. For example, differences in height, differences in weight, difference for that particular explanatory variable we are looking at. So if we look at, assuming we've collected water quality at different points, and water quality we've collected from the edge of the river, from the bank of the river, and we are going inside. So we will find that among those things we've collected is the color of the water. As we move away from the bank to inside the river, you find the color changing from dirty water to clear water. So we want to find out what influences the color of the water. Is it the added rubbish that is being added to the river? etc. We have measured many variables and want to find out what influences water quality. Okay, so we are looking at quality in terms either of presence of E. coli, presence of other things that we measure under water quality, but we are looking at presence of E. coli versus the color of the water. So color is categorical, and amount of E. coli present is continuous. So we want to find out overall, are there differences in the color of water as we move away from the bank of the river? I'm trying to get some Some examples in natural resources. Okay. Okay, so I have a question here before I continue to another slide. Can you say something about discrete data? Discrete data, those are counts. I've said they are obtained by counting, for example, number of birds, number of participants who are attending this course, number of people suffering from COVID, number of people that like corn maize or corn or maize, whatever you call it. And then please explain explanatory variables. Explanatory variables. So when you conduct an experiment, there are some variables that you can vary at will. Okay? So those variables that you can vary at will, for example, species, you decide I'm going to work with 3 species. And then we have fertilizer, amount of fertilizer. So you decide you're going to measure 3 levels of fertilizer. So then when you apply species, when you apply fertilizer to the species, we are going to look at growth of those species. How do they grow over time? Okay? Then species and amount of fertilizer becomes explanatory variables. They are influencing growth. Okay? So that is explanatory variables. And other books of thought say explanatory variables are measured with minimal error. So that's how you can identify what is, if you're given a data set, can you identify an explanatory variable? Look through the data set. Which variables can be measured with minimal error? For example, species, of course, you name them. You can't even make mistakes in naming them. Now, amount of fertilizer, you will really measure with minimal error as compared to growth. Because when it comes to growth, it is a function of height, DBH, and other environmental conditions. That's why it is called response, because it is responding to all those factors. Okay, thank you very much. So let me to the next slide. So under analysis of variance, we are going to briefly look at the types of experiments. Then, because I cannot talk about analysis without you knowing what I'm talking about. That's why I'm talking about the types of experiments. My colleague yesterday talked about the principles of designing an experiment. From designing an experiment, he also talked about the different types of experiments. This is just a recap so that out of the blue, I don't drop date on you and say now we are analyzing a CRD, okay? So we are going to do a recap. A CRD is used when we assume that the background information or material can be controlled during the experiment. For example, in a greenhouse, we can control the temperature, we can control the amount of sunlight. In that case, when you perform that experiment, you would use a complete randomized design. Otherwise, if you can't control the experiment, if you can't control the experimental conditions, then we have to use another type of design. Okay? So the model for a CRD, that is the model. It is the YIJ is observed response from the ith treatment and the jth experimental unit. You remember you've applied a number of treatments to the different experimental units randomly, and then you observe the effect of the treatment on the response. So the response is an outcome of the treatment effect in the particular experimental unit. Mu, which is the mu you see, I hope you see my cursor, it's like a hand. Mu is the overall mean for all the observed response. Tau I is the effect of treatment on the response. Tau I is this T here. In Greek, they call it tau, and it is the effect of treatment on the response. E here is called epsilon, IJ. IJ means on the ith treatment and J is the experimental unit. So for every experimental unit, which corresponds to a particular response, we can calculate the experimental error. So the experimental error here, that is the amount of variability that has not been explained by applying the treatments. Okay, so when we conduct our experiment, we apply the treatments to the experimental units, observe the response. When we bring our data back to our offices or wherever you see it, you are now able to tell how much of the variability in Y has been explained by putting the response. Applying the treatments. So this part here is what is explained. Mu and tau has been explained. But epsilon, that is the amount of experimental error, which helps us to determine the mean square error, which is the variance or variability of the experiment. So experimental error is very important. It also helps us to calculate, first of all, the standard error and the standard deviation of the experiment. We are able to know the precision of the experiment. We use the experimental error to test the effect of treatment on the response. Okay. So that is the model. In statistical terms, you can actually, when you do analysis, you can fill in these values. You can fill in mu, you can calculate mu, you can calculate the effect, and also the epsilon. Hypothesis. So when we conduct our complete randomized design, the hypothesis we are testing, the statistical hypothesis, just like my colleague said, mu A is equal to mu B is equal to mu C is equal to mu D. Mu A, B, C, and D are the different treatments you've applied. So we are saying that overall, there are no treatment effect on the response. Overall, there are no treatment effect on the response. But assuming we are dealing with growth and the different species, we are going to say that the average growth, there is no difference in the average growth. That is also a statistical hypothesis. We can say growth does not vary with species and deviate from the statistical hypothesis. Okay, alternative is that not all means are equal, or at least one of the means is different. So here we can change it and say growth varies with species, or type of species influences growth. Because we might now want to write hypothesis in your proposal or your concepts or your report when you are after analyzing data. So we can say species influences growth, or growth varies among the different species. But the hypothesis you see here is called a statistical hypothesis. And as a statistician, I don't mind seeing this hypothesis. But scientists want to see hypothesis written in terms of your research questions. So look at your research questions objectives and formulate the hypothesis. Okay. So we've said analysis of variance is a statistical technique used to compare more than two population means by isolating the source of variability in the response. The source of variability is divided into total variation, treatment variation. Within treatment variation is called residual or experimental error. So what do we have here? We have a response with total variation, 100% variation. And we've applied our treatments to the experimental units. So the treatments take up what we call it explains treatment variation. And whatever remains is called residual or within treatment variation. Some books call it error. Others call it experimental error. Okay? Anova model compares means among groups defined by a categorical variable. Anova and regression are both special cases of the general linear model. The model I presented here is called a general linear model. In regression, instead of having mu, we are going to have the intercept, which is denoted as beta naught, and the slope, tau I would be the slope, which is denoted as beta I. And we will have still epsilon. So regression and Anova and experimental design are almost similar, only that here under regression, both the response and the explanatory variable are continuous. In Anova here under experimental design, the response is continuous, but the explanatory variable is categorical. But they are a special case of a general linear model. And under the general linear model, we have assumptions, which we are going to see later on. Okay, so this is the one-way analysis of variance. Why do we call it one-way ANOVA? Because we only have one factor called treatment that we are dealing with. If we had more than one factor, for example, we have type of fish, and then amount of feed for the fish. Let's say feed fish. Okay, food for the fish. So we have the type of fish and also have the food, the different types of food that we are feeding the fish, and we like to determine which particular type of food helps the fish to gain weight very fast, and which type of species will actually gain weight faster so that we can put them on market. Because the most important thing of rearing fish is not just consume them, but we need to get some money here. Okay? So if we had two factors, then we would call it two-way analysis of variance or ANOVA. But because now here we have only one treatment, one factor, we call it one-way ANOVA. And the analysis of variance table you are going to see in R is going to look like this. Not exactly with squares and well neat as you see, but it's going to consist of the same things. So let's concentrate on this analysis of variance table. If you're given a data set, can you fill in these things that we see here? I would say yes. So under source of variation, we have the factor, treatment. So here I would fill in species. Then we have error stock residue, then the total. So these consist of the source of variation. Then under degrees of freedom, for us to compute the degrees of freedom for the one factor we have, we look at the number of levels in that factor. Now, we have treatment as our factor. The number of treatment is the same as the number of levels in the treatment. So the number of treatment, we've represented it as hash T, representing the number of treatments. Minus 1 gives us the degrees of freedom for treatment. Why is minus 1? I think that one we know. Let me see in the chart. Why do we subtract 1? Can we know why we subtract 1? Yes, somebody says we lost 1 degree of freedom. How did we lose 1 degree of freedom? Somebody is saying number of treatments, degrees of freedom. Why do we subtract 1 to get our degrees of freedom as T minus 1? Because of one treatment. Let me get, we are doing sampling. Okay, more. We have already used 1 sample. We've lost 1 degree of freedom. Okay. It's 1 treatment, 1 parameter. Okay. Okay, let's go back to the table. When we are computing, let me use the layman's explanation. If you have 4 observations, you have 4 numbers. Let's say 1, 2, 3, 4. But you go for a quiz, they only give you 3 numbers. What would you need to compute the 4th number? You have 3 numbers. Let's go to the chart. so that you don't ask me anymore about degrees of freedom. You have three numbers. I'm going to type. We have three numbers, 1, 2, 3, 4. Assuming those are the numbers we are supposed to have. And the total would be 1 plus 2, which is 3 plus 3, 6 plus 4, 10. Okay? So those are the numbers. Assuming you go for a quiz. Now this is the quiz. In the quiz, we are given 2, 1, and 3. Then they say find the fourth number. So ladies and gentlemen, we have, somebody has already answered. What do we need to find the fourth number? He has already answered. He says the mean and the total. Okay? So for us to compute the fourth number, we need the mean and the total. Meaning that without the mean, we can't even compute the total without the mean. Neither can we compute the mean without the total. So for us to compute the fourth number, we need the mean. So we lose one value, that is the fourth one, to the mean. So the only values that we are free to calculate are only 3. So we only have 3 degrees of freedom. 1, 2, and 3. To guess independently of any constraint. The fourth value, you have to know the mean or the total. That's why they call it degrees of freedom. Okay? Because you have one information lost in computing the mean. So then the only values you can compute freely are 1, 2, 3. Or the only treatments you can compute freely are treatment 1, 2, 3. So that's why we call it degrees of freedom. So even in computing the sums of squares, we are not going to talk about formulas. We need the mean. So the mean is important. So we lose information, that is 1 degree of freedom in computing the mean. That's why we call it t minus 1. And the mean is a parameter. So remember, when we come to error, we are going to talk about number of parameters. So let's concentrate on the first row here. So we know that the degrees of freedom for treatment is t minus 1, number of treatments minus 1, sums of squares. That is the amount of variability accounted for by applying treatments to the experimental units. Mean square is a ratio between sums of squares and degrees of freedom. Okay? Mean square is a ratio between sums of squares and degrees of freedom. Let me move down before I go to the F ratio. Error stroke residual, degrees of freedom. Here we only had one parameter, which is the mean, the population mean. Here we have 4 parameters, the treatments, if the number of treatments correspond to the different types of parameters. So the degrees of freedom here, for each treatment, we need to calculate a different parameter. That's why we are saying n minus t. Those are the degrees of freedom you have. N minus the number of treatments whose parameters are being computed. So that's why the degrees of freedom for error is n minus t. N is the total number of observations and t is the number of treatments. Then the sums of squares, there is a formula, but now that is the amount of residue or error that remains of the total variation. So if we get here our total variation, subtract the treatment variation, you're going to get the sums of square due to error. The mean square for error, which we call MSE, is sums of square error over the degrees of freedom. This mean square is the variance of the data. The square root of mean square gives us the standard deviation. Okay, so if we want to compute the standard error for any treatment, we need this value. the mean square error. Now, the F ratio is a ratio of treatment mean square over mean square error. That is the F ratio. And we can get a corresponding p-value. Okay, so as we do practicals, we'll be able to get these things and interpret them, apply some research on them. Okay, any question about this table? Because I move away from this table, why don't you ask me, why am I talking about this table? Why do I talk about this table? Because when you come to analyzing your data, you can check out and find out, are my results correct? For example, if you have 5 treatments and you get degrees of freedom 4 here, that means you have a mistake in your analysis. That's why you should know how to compute this table. I know the computer is going to do everything for you, but you need to know what to do so that you don't get garbage in, garbage out. You don't get wrong things. So you need to check out, is this information correct? Is this output correct? So that's how we check out, okay, the Anova table. Okay, let's go to the next. And how much time are we left? I don't want to go beyond. Okay, we have around 25 minutes left, so let's go ahead. So we've talked about the hypothesis that overall there are no differences in the growth, the average growth among the species, versus overall at least one of the means is different, or the growth varies with species. If we talk about fish, the fish weight varies with the amount of food or the type of food or the species of fish. Okay. Okay. So we've been looking at a dummy Anova, something that doesn't have figures. Now here I have an analysis of variance. This data was analyzed, is the same data we are going to use. And I want us to look at this table so that when we go to R and get an output, you know what it means. So our hypothesis we are testing a hypothesis that overall there are no differences in the growth of trees among the species. So we remember that when we are testing hypothesis, we state a significance level. Significance level is the smallest probability where we assume the null is correct. So normally we state a significance level of 5%, meaning that every time you conclude that there are differences, 5% of the time there are no differences. Okay? So the significance level is the probability the null is assumed to be correct. So at 5%, H naught is right, is assumed to be right. But when we conduct our analysis, when we perform an analysis, we look at the analysis table and we are able to either reject or do not reject the null hypothesis. Okay, so let's look at the output. TRT represents the treatments that were applied. There were 4 species, and the total number of observations here, 23 plus 1 gives us 24, and n minus the number of treatments is 24 minus 4 gives us 20. So you can check your analysis to find out whether it is correctly computed by the software you're using. We talked about sums of squares. There are formulas. If you want, I can refer a book to you later on where you can go and pick those formulas and read for further studies. But we said that the mean square is the ratio between sums of square and degrees of freedom. So you can check out with your phones. There is a calculator. You can divide 1291.5 by 3. We'll get this value here. And when we get 455.3 divided by 20, we get 22.8. Now, F is a ratio, and when we divide mean square treatment and mean square error, it gives us the F value, which is 18.91. Now, with only the F value, we can make conclusions about our null hypothesis and alternative. But since we are given a p-value, let's concentrate on the p-value. Now this p-value, it is the probability from the data. We remember we've said that for our null to be assumed to be correct, our p-value is 0.05. But then the data set says that the p-value is 0.00. R gives you the exact p-value. It actually calculates all the decimal places and gives you the exact p-value. Now you see that if we were at a 5% chance that the null is assumed to be correct, the chance has reduced to 0.00000, maybe 0.1%. Yeah? So if our chance that the null is assumed to be correct has reduced, that means we have evidence to reject the null hypothesis and conclude that at least one of the means is different. We conclude that the growth of the species varies. Or we say that growth varies with the different species or among the different species. So that's the p-value. That's how we conclude. Now, assuming our p-value was 0.5, I'm repeating, assuming our p-value was 0.5, remember our significance level is 0.05. It is at 5%. That's what we've stated. Now, if we get a higher p-value, that means the chance that the null is assumed to be correct is increasing because your calculated p-value is 50%. So you have no evidence to reject the null and conclude that actually growth does not vary among species. Probably there are other factors that actually affect growth. So you need to go and do more investigation. So I'm giving you scenarios, two scenarios, one from the real data where our p-value is 0.000, and we are saying that because our chance to support the null hypothesis has tremendously reduced, we have evidence to reject the null and conclude otherwise that growth varies among the species, or weight of the fish varies among the species. Or we can say weight is influenced by the type of food that is fed to the fish. Now, once we get a significant p-value under the Anova, we do not end at the end of the story. What we do, we go ahead and do pairwise treatment comparisons, or people call them multiple treatment comparisons. But we can also do contrasts. It is also another way of testing the treatments. Once you have a significant and also variance, okay? So the story doesn't end here. Once the p-value is smaller than 0.05, you reject the null, and then you go and do pairwise comparison tests, or we do contrast, depending on what you understand best and depending on whether you had pre-planned questions. So contrasts are used when you've planned those questions way hand at proposal stage. Don't wake up when you're analyzing your data and say, now I'm going to use contrasts. Okay, so you should have planned those questions. The comparisons should have been planned. Otherwise, it is the best way to compare the means, contrasts. Okay, let's go ahead. We shall see contrasts later. Okay, so this is explaining the result. There was a significant effect of species on growth of trees. You see, you can write, now it's about English, playing with the words. If you have very good English, then you can twist the English so that you can write it in different ways, okay? Okay, so I talked about treatment comparisons. So after the p-value is significant, we go and find out which particular treatment has the highest growth. And is that growth significantly different from others? Okay, so multiple pairwise comparisons are many. I've just highlighted only least significant difference, which is called LSD, and it's mostly commonly used. You will find that most of the manuscripts have, or published articles have, LSD or Turkey or Bonifera. There are so many. So this LSD has a simple formula here. You can see T alpha over 2, this is a value obtained from the T distribution table. You multiply with the mean square error from the analysis of variance table. You remember I talked about the mean square error. This is the one you pick in bracket over 1 over R. R represents the number of replicate for treatment I plus 1 over the number of replicate for treatment J. We are assuming we are comparing treatment I and J. And this is the standard error of that difference. You see here calculated as MSE over 1 over Ri plus 1 over Rj. R is the number of replicates. How many times is treatment I appearing throughout the experiment? That is the number of replicates. Now, under LSD, we get the average values for treatment I and the average values for treatment J and subtract. Okay, yes. Okay, let me finish this. Okay, yes. So, if the absolute value of the difference between the means I and J are greater than the calculated LSD value, then we reject the null, which says that there are no differences in the average growth of the two treatments. But if the absolute value, absolute means without any sign positive or negative, is not greater than LSD, then those two treatments are not different. So we are going to end here. Why do I end here? We have a questionnaire. We have an evaluation. And when we come on Monday, because people have complained on Saturday, and we cannot go against your faith to teach you on Saturday. So we are going to resume on Monday. So take a break and you go and pay allegiance to God. Okay, and pray to God to give you wisdom, knowledge, understanding, everything He gives. Yes, He does. Okay, and then we'll meet on Monday. Monday, I'll do a recap, and then we start from there. And we are also going to do our practical of what I'm talking about. Okay, so the questions that have been raised, interpretation of p-value, I'll not do them now, but when I come in, I'm going to keep these questions. Don't worry, I'll not forget. I'll remember them. They will be in my bag. I carry my bag with me and come with it and then answer those questions. So now my colleague Helen is pasting the evaluation in the chat. Please pick the chat. I am going to stop sharing so that you're not influenced by what you see, but you answer as what you think. Please make sure you fill in that evaluation form within these 15 minutes. We need your comments. We need to tell you, we need to tell us, what do you think? Maybe we need to change the way we are delivering. Plus, make sure that you register. I have been posting the registration for day 5. Make sure you register. It is important for the people who are funding this course to know that actually it is true you are in the course. It's not that we made up and sat down and we pretended that we had 560 people that I can see here, yet they were not there. Okay? Pardon? So, Dr. Helen is posting the monkey survey, so don't worry about sending it anywhere. Once you finish answering the questions, just submit the monkey survey. And the registration also, just submit. You've been such patient and great participants for the 5 days. We've enjoyed talking to you, sharing our knowledge, laughing, smiling. Though we don't see your faces, we know that you're smiling back there. And you're also understanding what we are talking about. Okay? So I'll keep around until the session ends, but Dr. Helen, please keep posting the evaluation. Yes, I can see that Khan is Thank you so much. Thank you very much. And I am so grateful that you've given in 5 days of concentration and attending to different things at the same time. Today we gave you survey and we are now giving you experimental design. Okay? You're welcome. You're welcome. And please practice. Don't just keep these things. Practice with R. You need to practice with statistics. We need to practice. Apply the knowledge. We are also going to do an evaluation on you. How is this evaluation going to be conducted? We are going to ask you to present what you've learned and how you've applied it to your research. So please, as you go in the weekend, Saturday, Sunday, I know you're going to pay allegiance to God. Those who are doing it on Saturday, they do on Saturday. So on Sunday, you're free. Those who do it on Sunday, Saturday, you're free. So do the assignment so that next week, you've made a simple presentation for us to look at and see whether you've really benefited from the 5-day, from the 10-day course that has been organized by Forum and Mercy and World Bank. Okay? Okay, we have 10 minutes to go. So please make sure you fill in those things. Fill in the evaluation, fill in. Yes, thank you, Kathy. We are grateful that you appreciate. We are really grateful. Thank you for your comments. Thank you. I am happy that you learned. Yes, there is an attendance form. It has been posted. Please, Helen, can you post it again? Okay. Yes, thank you. It has been effective. What are they typing? Oh, okay. Thank you. Please pick it from the chat and put it on Telegram. We haven't joined Telegram. Please post it in the Q&A. Helen, please post it in Q&A so that people can now post it in the Telegram. Even the registration form has been posted together with the evaluation form. If it wasn't that you people get tired, I would talk the whole day up to 5 and we laugh and talk, but you also need to understand, so I can't really continue bombarding information to you and you're not picking. So we need to let you go and revise, and then we will meet on Monday. So you have 7 minutes to go. So please go and upload, not upload, but download. Yes, that is the right English word. Go and download the information or Google link. The table that I presented, I am going to post it on Google link so that you can receive that table. And it's a quick reference for you when you're looking, what type of analysis can I use instead of running to a statistician? If you run to me, I do what I think, not what you want. So remember that when you run to a statistician, she will do what she thinks is right, not what you want. So always try to do the work yourself. Try to go to the field yourself. Don't delegate. Okay? As a piece of advice, as a student, don't delegate your work to others. Go to the field, collect the data. You will know the mistakes you make. Even when it comes to entering data, participate. And when it comes to analysis, do it yourself. I'm told the monkey survey is slow, so I request David Amitu, Dr. David Amitu, Give me more 10 minutes because the monkey survey is slow. So hopefully David has heard and will not switch off at 2 so that the monkey survey can be done. Okay? Thank you for those who have already completed the monkey survey. Make sure you also complete the registration form.
You're free to continue, Prof.
Day 1 attendance is when you registered. So don't worry about day 1 attendance. The registration you did when you're joining the course is counted as day 1. So don't worry about it. Attendance for day 4, can you send day 4 attendance? If you have a question, post it in the Q&A because the chat, many people are pasting, commenting, and we lose the questions, yes? Okay, all the attendance from day 1 to day 2 to day 5 will be included in the Google Drive. So you can upload and register, okay? Thank you for everybody. Thank you to everybody. Thank you, participants. Thank you for those who have already completed the survey. Please, everybody should complete the survey because we'll be able to know how many people completed, although we don't see the names, but we'll know how many people completed the survey. So please, complete the survey. It's important for you and me, okay? You're welcome. Okay, thank you for completing the survey. Thank you. Okay. Okay, training certificate. We'll talk about it next week. But you will get, I'm told that you will get the training certificate. Yes. Is there anybody who is not yet done? We have 3 minutes. And if you have any question about today's presentation, keep it. You can post it in the Q&A on Monday so that we can answer the question. I've kept these ones, we'll answer them on Monday. Please use the Google link. All the materials from day 1 are there. Also go to YouTube and listen it because it has been recorded live. Even now, if you went to YouTube, you would see all the 3 days, all the 5 days are there. So download the videos and then you can now listen to them and catch up for next week. You put them there. Okay, Dr. Helen says that she has put the YouTube links. Oh, she's going. Sorry about that. She's going to insert all the links for day 1 to day 5 in the Google link so that it is accessible to everybody. We have 2 minutes. Anybody who is not yet done? Okay. Okay, I would like to thank you. 1 minute to go. Thank you so much and have a great weekend. And when we come back, bring more people in, but advise them to go through day 1 to day 5. Thank you. And I want to say bye. Bye-bye. Have a great weekend. And thank you for being excellent participants. Bye-bye.